Hello there, welcome to the wonderful world of radio frequency and electronics engineering. On the bench today for repair is a BNOS UHF RF power amplifier rated at 50 watts with just 3-4 watts drive. We're going to look at this amplifier in depth. You join me after what has already been the video being filmed and the repair being completed. So what's coming up in this video is we're going to use a spectrum analyzer in a very detailed way, measuring not only the transmit power amplifier itself when we do the repair and analysis of that, but we're also going to be using it to measure the low noise amplifier, which is an option that's installed in these to improve the receiver signal strength. And also we're going to be using sweep measurements, sweat frequency measurements. We're going to be using RF attenuators such as this in order to make fundamental RF power measurements on the spectrum analyzer, basically turning the spectrum analyzer into a fully fledged RF power meter. We're going to look at harmonic analysis as well on the spectrum analyzer, both low noise amplifier within the unit and the transmit power amplifier, which is made of bipolar devices. We're going to reverse engineer some of the circuits and go through some of the circuit theory. We're going to use the Marconi 2968 radio test set as a drive source and the HP Agilent ESA series spectrum analyzer in many different ways. We're going to look at system losses, calculate that, show you how to go about setting up the spectrum analyzer with RF attenuators and calculating the system loss of attenuators and associated test cables and factoring that in and changing the settings on there to do the measurements that we'll need, and using the sweep function as well, show you that in conjunction with aligning wideband low noise amplifier, and then we'll come full circle and finish the video off with the final harmonic analysis. So stay tuned, I'm sure you'll enjoy. Hello there, welcome to the wonderful world of radio frequency and electronics engineering. On the bench for repair today is a BNOS UHF RF power amplifier. This RF amplifier boasts an output power range of up to 50 watts on the UHF frequency bands, roughly between 430 to 440 megahertz. This amplifier works on 12 volts DC, draws up to about 20 amps depending on the RF output power that it delivers, and we're going to use some radio communication test instruments today. The Rohde Schwarz CMS33 radio tester, more than likely, in conjunction with some RF power meters that we've got. Now, we've got a couple of RF power meters here. We've got the Bird through line watt meter, which is model 4304. This particular meter measures up to 500 watts from DC to 1 gigahertz without any pods. It's also got the sample port on the side, so that we can connect that off to spectrum analyzers and things like that as well, such as the HP Agilent spectrum analyzer. We've also got another version which does measure more accurately, and this again is made by Coaxial Dynamics, and that's this one. Now this meter is based on the Bird through line. It's all part of the same company, but this is made by Coaxial Dynamics. This one is based on the model 43 meter, and then in the back we've got some slugs, but we've also got a case with the Bird 43 in it and lots of insert slugs to go in the compartment here, so we can measure RF power more accurately on this meter than we can on that. This has a higher accuracy than this one on the right. The only reason why I've brought these out as an example to show us making these measurements is that sometimes when these RF amplifiers have problems and they don't key up into transmit fully, and they sometimes break down as they're transmitting in the initial phase, so they'll key up at full power and then suddenly they'll just fall off, or they'll have an intermittent spurious output. We can capture that on an analog meter, whereas on a radio test set such as the Marconi or the Rohde Schwarz, the test set needs time to lock onto the signal and then be able to measure the RF power and then display the analysis on the display. So if the RF power is divvying up and down for those initial few seconds while the test equipment tries to latch on and make that measurement, then we've not really seen what's gone on. whereas with an analog meter such as a Bird 43, we can see the needle moving. We know that it's producing an RF output power on a frequency or multitude of frequencies. Again, if these amplifiers are producing spurious emissions, the test set frequency counter is trying to lock onto many different frequencies, and then it'll not read the power until it's locked onto a particular frequency. So again, little intermittent faults and things like that can be more difficult to detect on a radio test set than they can be on the, say, RF power meter. Additionally, we can put attenuators on the output and then reduce the output level down, assuming that it's 50 watts. So for example, we could put an attenuation level in that would attenuate 100 watts down to a safe level for this particular spectrum analyzer to be able to measure it, and then we can use the spectrum analyzer to make a power measurement as well, taking into account the attenuators, and also we've reduced the level to such a safe level where the spectrum analyzer can read it. So that's one of the advantages as well about this Bird meter here, the Bird 4304, which it's got a sample port on the side, that yellow port there, and it's fallen over. So that's it there. We can connect that off to a spectrum analyzer if we need be. These are nice little meters, been around a long time, and as I say, they measure up to from basically HF band right up to 1000 megahertz. Measure both forward and reflected power as well for antennas, etc. So they're quite a useful piece of kit to have. Quite old-fashioned in comparison to, you know, the Bird 5000 EX power meter that measures digital modes as well, such as P25, DMR, Tetra, D-Star, Fusion, Moto Turbo, and pulse radar applications. But we don't need that in this case. We just need the standard Bird 43 models of meter or the radio test sets. So what we'll do, we'll power up the amplifier in a minute, and then we'll take a detailed look with the radio connected to it. Now, these amplifiers are commonplace, particularly in amateur radio circles. But if we take a closer look at the amplifier, this has a few features. It's if we switch it on a moment, which it is, in linear mode, it means that this will then become an amplifier. We've got a preamp as well, so in other words, it's a low noise amplifier for the receiver. So it not only amplifies the transmitter signal, but it also amplifies the receive signal coming in from the antenna to the receiver by maybe as much as 10 dBs. We've got an RF output power indicator here, obviously, which gives us information about the level of output. And then on this side here, we've got a switch which is detailed FM and SSB, because this amplifier also deals with SSB radios as well as FM, for single sideband being upper sideband and lower sideband radios. So obviously it's useful for that, and we'll look at how that works when we get the lid off. Round the back, it's a fairly big chunky sort of amplifier, not something you want to drop on your foot, otherwise you'll end up going to the hospital. But we've got an antenna output. I've got a BNC to N adapter screwed on at the moment. So we have an N-type, type N for the output for the antenna, and then for the transmitter, again, another type N, 30.8 volt DC input, and we have a remote press to talk manual key, if we like, to key the amplifier into the transmit mode. For example, if we're using this with CW modes on the UHF band, where we have a transmitter, QRP transmitter, sub couple of watts, that's keyed manually using the Morse key. So that is why that's added. Or a manual switch, you know, if you want to key up the amplifier using a relay switch within the radio itself, that's also possible without the RF detect feature, which we'll look at next. Plenty of heat sink on there, lots of cooling, you know, it could last a long time on transmit before it would overheat. Underneath, again, just a standard bottom enclosure with the feet on it. Power cable, the fuse, inline fuse as well, which is always good, because some of these amplifiers have a fuse holder in the back as well. and often the cap on the fuse holder gets lost or drops on the carpet when you're changing the fuse and never seen again. So yeah, BNOS have been around a very long time. They've been well placed in the market and a very established manufacturer of amplifiers for a very long time. A little bit like microwave modules, which you'll have seen on my YouTube channel, very similar looking amplifier. Okay, so we'll have a look inside and see what information we can find out about it. Okay, so we've got the lid off now, so we can have a look inside before we do some testing. As I said, this amplifier came to me with a report of no output power at all on UHF, and it's been driven with some power, so we'll do some checks on that very shortly. But I just thought it'd be quite interesting just to have a look at its architecture and have a look inside, and let's go through the theory of operation. I haven't been able to find a service manual for this or any diagrams or anything, but well, we'll just have to see what we can work out ourselves here. So with a look of it, the positive and negative supply lines coming here. The negative supply is connected, or the 0 volt supply is connected here to the stitching and this ground plane, which is this this massive track here, which goes off obviously all the way along this print, all the way along to the emitters of all these transistors. So the very corners of these transistors are the emitters, these legs here. And we've got bonding through the board, which is why we've got these holes through to what is a copper clad across the entire PCB on the other side. And again, the emitters on both sides of these transistors, top side and bottom side, are bonded via the stitching through to the underside of the board. And also the screws that bolt the transistors down, the RF power transistors, have also got little like eyelet connectors that bond the actual emitters of the transistors directly to the heatsink and the chassis of the device. And this is why it's very important to keep the distances as far as physical lengths of track to minimum, because obviously UHF frequencies, very small distances end up being quite large inductances. So by having the wire as close as we can to the screw which bonds it through to the chassis of a device and the heatsink, as well as the stitching that goes through the board to the underside and screens that, as well as the emitters of the transistors, means that the possibility of instability is vastly reduced, because we get undesirable effects when we get inductances at UHF frequencies. The parasitic inductances can cause havoc with designs. So that's why they brought it straight there and soldered it to that part of the circuit board. Down here we've got a positive supply line which goes to this island here. As we can see to the left, we've got an electrolytic capacitor which is used to smooth off any transients on the supply line. We've got a large silicon diode here, rated probably around about 30 amps in current capacity. And what this does, if the polarity is reversed by accident, then it short circuits the input and obviously pops the fuse to protect the device. But obviously there's no signs of any damage on that at the moment, so I'm fairly confident that's not happened to this device yet. Now, insofar as the supply lines are concerned then that go to the rest of the device, from this capacitor, the junction of it, which is a main plus supply line coming in, we've effectively got a few branches here. We've got a branch which comes off directly underneath the capacitor downwards and along, and also we've got another track which comes under this resistor and then goes down here as well, there in that angle, as you can see. So these two tracks carry supply voltage, but also this larger track here carries the supply voltages to both the final output power amplifier transistor and the driver, because we've got a radio frequency choke here that goes across to this island. Now we have various capacitances on here. We've got an electrolytic again to help smooth any transients on the supply line, but we have some capacitors which are a much smaller value, and different types of capacitor chosen specifically to choke off any RF coming back from the collectors of the RF power transistors, because the DC potential has to travel through the RF chokes and these radio frequency chokes to the collectors of the transistors. These are bipolar Motorola power transistors. And on the collectors is where the RF is effectively swinging or is switched. So basically it's in class C mode when it's in FM, and there's bias voltage applied here by these resistors etc. in this biasing network when it's in SSB AM mode. And we've also got some negative feedback here, which I'll speak about shortly. But basically this transmission line here on the collector has both DC and RF power on it. So basically the DC supplies to get to the collector, but we don't want RF coming back, because if RF does manage to get back onto this supply line and it makes its way along to this transistor, you can get an oscillator going basically. It'll produce all sorts of very nasty things. So what we do is we use a radio frequency choke to suppress any RF coming back while allowing DC to supply the collector. But on this island here we've got to choke off any RF that's managed to leak through this RFC. So these capacitors here, this green one and yellow one, as well as the electrolytic, which is more suited for the lower transient frequencies for the power supply. These two are mainly used for the RF. They choke off the RF, and then we have another radio frequency choke again, which then suppresses any more RF which potentially could come back. Again, as the supply line moves along, here we've got another radio frequency choke, which is this coil here. Again, same topology. We've got an island here, same capacitors again, the 3 capacitors we've got there. Another radio frequency choke, and then that goes to the collector of the driver transistor. So that's where we've got the same design as what we've got on the power transistor side. Now, on the RF side now, as we can see, we've got the supplies going off to various places, but on the RF input side, on the right here, we've got the RF input socket, which is a type N. You'll notice that there's a coaxial cable soldered directly to the inner and outer, so there's no circuitry in this area. Some amplifiers do carry that, but on this design it's just a simple coax. And then what we have, the coaxial cable comes along here, goes round up under this flexi circuit and solders here, and that's the RF input, which goes directly to this relay. Now you'll notice if you look in this area here, there's actually some components, some resistors, some diodes, an RF, what we chose, a capacitor for the what would be the rectification, smoothing of the RF power that's coming in here from our drive source. Now you'll notice they're using a directional coupler design, because if you look very carefully just here, there is actually a track which runs very close to the larger track where the coaxial cable solders to. And you'll notice that there's some diodes and some resistors here which are employed to rectify the RF. So this is essentially a directional coupler or a sniffer. So this picks up without directly influencing the RF that's coming in or loading it. It just loosely couples RF from the main track here to the coupler, and the diodes rectify. These are Schottky diodes, high frequency switching diodes, capable of switching at UHF frequencies. So these rectify the RF into a DC potential, and that's smoothed by this capacitor, and that's then fed off by this potentiometer here, which I believe sets the trigger level for the logic circuitry here to then energize the relay in order to switch the RF into the path coming out here on this track, which then goes into a pi attenuator. And the job of the pi attenuator, which is comprised by these 3 resistors, is to provide a certain level of dB attenuation, which then would supply the correct drive level of RF to this driver transistor. And so there are a couple of things that have to go on here. There's the detection of the RF, which is paramount, because obviously in the current state that the amplifier is in when it's not being driven with the transmit RF power, it needs to connect both the inner of this coaxial connector here and the inner of this coaxial connector, which is the output. So both basically the input and the output connectors are connected directly together via the relays. and when it senses transmit by that directional coupler, it then pulls the relays in to then divert the incoming RF path through the relay, through the pi attenuator and into the driver transistor. Obviously it amplifies up through the output transistor, and that then is fed into this relay, which is pulled in to connect this track to what is the output connector. In receive mode, when we're not transmitting, obviously the relays will de-energize and the RF path would connect via these two relays back through directly without going through any amplifier circuitry on this side with the transmitter. Would be connected back from the input to the output to the input, etc. So even when the amplifier is switched off, we can still transmit, we can still receive, because effectively the two aerial connectors, the input and output RF connectors, are actually connected together. So that allows us to use a transceiver without this amplifier even being powered. So that's one of the little features that these have got. Obviously, if we didn't have the relays and the output of this transistor was connected just to the N-type for the output, any received signal coming in would never make it back through these transistors back to the input connector to the radio transceiver. So what we must always do with these amplifiers is when in transmit mode, when it senses that using this coupler here, it must switch in these relays to make the RF that's coming from the transceiver on the transmit side come through this pi attenuator into the first stage amplifier. Second stage, the output then is switched via this relay directly to the output socket. But in receive mode, then these relays are effectively switched in together so that there's a connection straight through. So the input and output is basically connected together. Now on this design, there's a third relay here which is used as an additional ancillary function, which is for this low noise amplifier here, which we're going to test as well later. And this is used as, looks to me like a bipolar, sort of a BFR90, BFR91 UHF RF amplifier transistor. And this would provide an RF amp, low signal level RF amp, for the receive signal boosting. So any receive UHF frequencies that are coming in on this connector while we're in receive mode would then be further amplified by this low noise amplifier, this LNA, and then pass through to the inner this coaxial cable via this relay and then back to the input connector. And thus what that would do, it would then effectively amplify any received signals that are coming back into the amplifier. So there's a lot of clever switching going on with these relays, and obviously we've got the facility on the front of the amplifier to switch this low noise amplifier in or out, hence the reason why there's a relay. So we don't have to have that low noise amplifier in circuit or in use. We can switch it in or switch it out, it's up to us. So that's why that third relay is in there. So basically the RF path as we see it coming in here is then connected to this relay, detected by that coupler. In transmit mode, the relay gets energized and pulled in. The RF path comes out then on this track here through these resistors, hence the reason why we don't want to put too much power, drive it with silly amounts of RF power, because these resistors are only rated at a couple of watts each if you're lucky, and it'll burn them out. So we need to keep the RF drive level quite low. So they're obviously a pi attenuator. The RF level then coming in being attenuated is then connected to this capacitor, and we also have here, if we look very carefully, there's an inductor, a short piece of wire which solders directly to there, the junction where the RF signal comes in, and the chassis ground. So this forms basically an RF inductor. We've then got this variable tuning capacitor coming in here, which then allows us to tune this pi attenuator input circuit and the impedance obviously to the input of the RF transistor. So that's obviously on this strip line here, and then we've got another radio frequency choke, this time in a ferrite bead. That then applies voltage for our biasing, because when we're in SSB and AM modes we need the transistor to be biased in class AB mode. so we need to give it a bias current, which is set by these potentiometers down here, and the bias current then allows us to work with SSB and AM. When we're in FM mode, we don't need the bias, so therefore it will be in class C mode, so there'll be no bias on the base of this transistor. We've got another radio frequency capacitor, tuning capacitor, plated capacitor. We've got some capacitors again on the soldered across the base to emitters on each side, and then the RF power transistor itself. We have an inductor, resistor and capacitor arrangement, which is here, this green capacitor, this inductor, and there's a resistor just underneath the green capacitor. And what that is, that's negative feedback. So RF power that's being developed on the collector of a transistor is fed back as negative feedback to the base, and what that does, it basically flattens the gain of the transistor and gives it improved stability, so it doesn't then produce unnecessary, well, too many unnecessary harmonics, doesn't go into self-oscillation, doesn't run away at peaks of gain at one frequency and very little gain at other frequencies. So basically it controls the feedback, and it helps the transistor perform properly. We've then got down here a temperature compensation diode, which is this diode here that's sort of pushed up against some heatsink compound. This then provides the compensation for the biasing in class AB mode when we're in SSB and AM mode. The output of a transistor here on the collector, because these are bipolar RF power transistors, not FETs, again supplied by radio frequency choke. We've got some more capacitance on the collector, between the collector and the emitters on both sides, and then we have another radio frequency tuning capacitor here, another fixed RF capacitor, and then we have a series RF ceramic capacitor down here, which then blocks the DC, because obviously on this line right up to here we'll have 13.8 volts DC, and we certainly don't want that on the base of the next transistor, so we have to block the DC and allow the RF to pass. We then have the same arrangement as we did again on the base of the driver, where this time on the power amplifier, final amplifier, again we've got a beaded radio frequency choke which supplies DC bias to the base of the transistor in class AB mode for SSB and AM. We have a radio frequency plated tuning capacitor here which tunes this entire strip line and impedance matches into the input of the final RF power amplifier transistor, again a bipolar MRF646 Motorola transistor. We've got capacitance again on the base and emitters, and also negative feedback again with this inductor resistor capacitor arrangement here, LC arrangement. This time on the output we've got ceramic capacitors, which are high voltage, high wattage rated, high temperature rated capacitors, which solder between the collector and emitters on the collector, and again the same format again, radio frequency choke, supplying DC voltage and yet choking off any RF coming back. And then we have yet again another tuned strip line going along here to another plated radio frequency tuning capacitor that tunes the Q on this strip line, the output of which, again, because this is live at 13.8 volts DC, we need to block the DC and let the RF pass through. We've got a ceramic capacitor here, RF cap, that allows RF to pass through and blocks the DC, and then the RF output finally goes to this relay. The relay can switch in two configurations. It can switch into receive configuration, which will couple the RF back effectively to the other relay and then back to the input socket in receive mode, or via this relay to a low noise amplifier, or in transmit mode it will just simply connect the RF output power straight to this RF output socket. But if we notice as well, we do have on just on this section here another directional coupler which measures the forward power going out of the device. The reason why it measures the forward power is because the diodes are on this side, not that side. So that sends the output power going out, and obviously can control itself, and with the logic circuitry to make sure that it's performing correctly. Now in SSB modes and AM, there is a built-in delay as well to prevent the relays when there's no modulation on the carrier in between words or speech on a radio transmission, from deactivating the relays, and thus the relays chattering, coming in and out as the RF envelope is modulated. So there is a built-in delay in the circuit, an LC timer basically, that prevents the relays from de-energizing when they're in the transmit cycle, and that's done by a switch on the front. So again, the logic circuits here are all used for op amps and for controlling the gain and function of the device. This looks like it's there to set the input power, this potentiometer, for the directional coupler there. That's probably the trigger level that the logic will trigger. So you give it, say, 1 watt RF power, just this, till the relays click in, and obviously then it begins to amplify. Likewise on the output there's another potentiometer here, because if we follow the track, it's very difficult to see with these wires being in the way, but you might just be able to see on the output of this directional coupler here, there's a track comes down sort of just underneath this diode, and it comes along there, and that goes to that potentiometer. So that potentiometer sets the directional coupler sensitivity on the output circuit. These two, I firmly believe this one on the left will control the bias current to the driver transistor, and the one on the right here, this potentiometer, will control the bias current to this one on the power amplifier transistor there. Again, we've got on both transistors temperature compensation diode that's bolted or heat sink coupled to the transistors, so that the moment they start to get quite hot, then the bias current gets adjusted automatically. So this op amp circuitry is responsible for that. This here is also responsible for logic switching, and also for doing the functions with the SSB modes as well. Now the low noise amplifier, which is for receive side, so when we're in receive mode, UHF RF frequencies coming in here at wide band will go through this relay first, and in receive mode it will get switched onto this track here. You can just see it there, and it goes in underneath this relay. Now if we've got the amplifier switched in for the low noise amplifier and receive, the RF path will get switched through this relay and onto effectively this track here that's coming out just on the far left, and that will then go through the low noise amplifier, and there's a BFR 91, I think it is, transistor, which is just something like a 10 dB gain, something 4 dB noise roughly. It's not even a mimic, it's just a BFR. And this then, as its output, connected them back out on the output of the amplifier, there's an input track and an output track with a look of it there, connected to this relay. So if a relay switched in the amplifier configuration, the low noise amplifier for receive mode, then the relay contacts will go over, so the RF incoming signal will be fed in here, and then the output from the amplifier will is fed on this top track back into this relay. If we're not having the, as per the switch on the front, the choice for the receive amplifier selected, then the relay will just merely connect this track here that's coming from the output socket relay directly across to this track, and thus it would then obviously connect through the relay back onto this track here, and then go directly back then to the input socket. So in essence there will be a DC path, if you like, between the input and output socket, just a direct pass-through mode. So that's that little rundown. Now I think on the way that they've designed the low noise amplifier there, if we zoom right in, you can see that we've got some tuning as well on the low noise amplifier. We've got a little BFR device down there, that little black round thing. We've got some diodes and things that are present on the input leg to prevent any leakage of RF from the transmit side of the contacts on here from overloading the RF amplifier, causing instability on this or blowing it. So basically we've got Schottky diodes back to back on the RF input, which clamp the RF voltage, make sure that it doesn't exceed about 0.7 volts, otherwise it could damage the transistor. So microvolts, in terms of received signal strength being in the microvolt level range, will pass through into the transistor. We've got an RF inductor here to ground, which you can see here. Effectively it's a transformer, because we've got the incoming RF signal on the bottom RF inductor line, which transforms onto the top RF inductor line, which then obviously goes to the input of the transistor. And then the output, in essence, does the same with this line here, and then we get that coupled then onto the output leg with some more tuning going off. So we can actually tune this amplifier as well, so that'll be interesting to have a look at that a bit later. As regards the front of a device, obviously we've got a logic board, which if I zoom out again we'll be able to see that we've got a little logic board down here with the LED indicators on. Again, the bar LED display on the front is controlled by this device. So obviously as the RF power increases on the output, the directional coupler on the output there would obviously have a higher voltage as the output power increases, and thus the bar graph on the LEDs on the front will be appropriately lit by the outputs on this IC. So that's a little rundown, just basics of this amplifier. So I think now it's time to do some functional testing. Okay, so where we're at now is we've got the Calmus wideband DC to 1 GHz power amplifier connected. This has to be fan cooled for long operation because it's class AB biased. It's high stability, high grade power amplifier. Hence the reason why we've got the fan on top to keep it nice and cool. What we've done with what would be the connectors that go to the input and the output of the RF amplifier, we've actually got a pass through. So basically the N-type that will connect to the input as well as the output connected together, and that then is connected up to the Rohde Schwarz. So we've got an RF feed in there, which is the output of this Calmus amplifier at the moment, and then on the Marconi below we've got the SIGGEN. So basically the output of the SIGGEN on this cable here connects to the input of this Calmus amp. The output of the Calmus amp then, that's the input side, that's the output side, and that then connects to here. So basically we're going to drive this amplifier with the Marconi radio test set SIGGEN, and the output of the amplifier then is going to be read on the Rohde Schwarz. So that's what we're going to do now. So what we're going to do is we're just going to, I've got the RF gen set to 433 megahertz. The level's quite low at the moment. We're going to have to drive that amplifier, so we should see a reading come on here. I want about 3 to 4 watts roughly, so I'll just increase the RF SIGGEN now. And shortly I'm hoping, fingers crossed, there we are, look, so we're getting something. Just keep going till we get a power reading on the Rohde Schwarz. And there we go. So maximum signal level coming out the Marconi now is giving us, after the amplifier, 3.42 watts at 433 megahertz. I've got 2.5 kilohertz deviation modulation on there as well. So that's now producing RF power via these connectors. So I'm now going to switch the RF off and then connect these up to the amplifier, and we've got the amplifier powered as well at the moment. We've got a power supply. Oh no, I haven't got the power switched onto this yet, so I'm going to switch the power on now and then connect all these up and then re-establish the RF, and we'll be back shortly. Okay, so where we're at now then, we've connected up with the pink cable here, purple cable rather, coming in the RF input power from the Calmus drive amplifier. The black lead goes off to the Rohde Schwarz radio test set where we're going to read the RF power, but the Marconi SIGGEN at the bottom, when we switch that on, will then provide the drive to the Calmus amp. The Calmus amp will output about 3.8 watts into this, and then we should see, if we keep an eye on the front, an indication of RF power on the front, and we should also watch the CMS Rohde Schwarz radio test set for the power and see how much RF output. We should hear the relays click in when we turn the RF power on, so that should all work. I've just made sure that I've switched the RF power amplifier on. I've not got the switch in for the preamp, so I've left that switched off, but the TX power amplifier should come on. Now we should see some minor indication on here of RF power as well. So what I'm going to do is I'm going to press the SIG-Gen on button now, and then it hopefully put the transmitter into this amplifier into transmit mode, and then so there we are. Look, oh, suddenly all the LEDs have sunk. It's drawing 12.4 amps. We're getting a reading of about 7-8 watts, but I'm sure I saw more power coming out initially for the first second or so. Just have a look at that again. Yeah, look, 50 something watts, then plummets down to 10, 14, etc. Switch it off again. Just being careful, because this amplifier is actually drawing 12 amps. I'll just feel about here somewhere, see whether anything's warm. I've just switched the RF drive off. That PA transistor's quite hot. The driver's not too bad. There's no heat in this area really on the PCB where my fingers are, but certainly around that driver transistor, that power amplifier transistor. So I'll switch it back on again. It's in SSB mode. We've got it in FM mode. Let's put the power back on, but keep your eyes on the Rohde Schwarz test setup there, how much power it suddenly provides. Good 45 watts, and then it suddenly dies off, and then off it goes again. But yeah, when I look at the ammeter, which you can't see on camera, it's drawing 12.3 amps right now, so it's doing the same amount of current at the beginning. I'm just going to watch the current meter at the beginning, and there it is, 11 point something amps, 12.2 something. So it's not drawing less current as the RF drops away, or the current isn't changing as the RF drops off. So it seems to me, could be wrong, I'm only guessing here, that it could be an RF path fault rather than the DC conditions being incorrect. So I might start looking around here for dry joints, dry solder joints, things that may need adjusting. Now, I'll twiddle this pot first anyway to see if that's got anything to do. I don't think it is, because I think that's just the sensitivity for the RF power. So I'll just adjust that and see what we can do. So that's that way, yeah. So it sees there's RF power there, but there's not enough until we turn that potentiometer, and then suddenly it activates there. That's interesting. Every time it keys up, it does best part of about 40 watts or thereabouts. Yeah, 42 watts there. So that just sets the input sensitivity, that's all, for the TX RF power coming in. Right. I'm not sure what the other one does. I'm just a bit careful here because it is drawing 12 amps. So I don't want it burning out, because 12 amps is quite a lot of current, and obviously I don't want the circuit blowing up or whatever. But just touching around that PA transistor, there's a fair bit, not too much heat, but there's a fair bit. The heat sink's quite warm, or getting warm, so I might try adjusting this potentiometer next, but that might be something that I'll do a bit later, because I think this just sets the output indication here with that reading, probably 50 watts full scale. That probably just sets that up, what lighting level this will get to. It's probably nothing to do with the RF output power as such. The biasing, it's SSB mode is when it's in, FM when it's out. Let's just try it with SSB mode. So then it's in class AB, and these power transistors will get bias. So let me just turn the RF on again. Now it's still doing the same again, just a bit of a delay, that's all, when you unkey the transmitter, which it should have on SSB. So that's not having a bearing on it. See, it suddenly bursts into life at 48 watts, and then it just falls away. So it's trying to do the power. It's trying to do the power. So there's something somewhere not working quite right. Now whether it's just some issue with the relay, or whether it's dry joint somewhere, something like that, I'm not sure. It could be the transistor even maybe breaking down. It could be a number of things, so we're just gonna have to have a look round and see what we can see. It could be tuning as well, potentially. We might be able to get around that though by setting the frequency on the radio test set. So if I go to RF gen on their frequency and then set up, instead of being on 433, let's try 430 megahertz, just to try a different frequency, just in case it's going a bit unstable, you know, at that 433 megahertz frequency. So let's try it again. No, it's still doing the same thing at 430 megahertz as to what is it at 433. Yeah, there's something strange going on, but what's interesting is the current isn't changing. So that's interesting, is that? Right, I'll just have a closer look and see what we can find. Okay, so what I've done now, I've removed the cases to these relays, all three of them. They just pull off quite easily, so that's a bonus. And now we can get to the relays. What I want to do is just check the continuity of the contacts on these relays. So what I propose to do, rather than drive it the RF, obviously RF power would seriously damage or upset the voltmeter on ohms. So we don't want any of that funny business going on. So what we've got to do is we've got to remove the RF connector, because we don't want to connect our ohm meter connections, which I've got a bit of a lead I'm going to rig up, because obviously the slight voltage comes out of the voltmeter in order to, you know, do the ohms checks. So we don't want that going back up to the test set and causing any damage to that, because spectrum analyzers and radio test sets don't like DC volts fed up them. So what I'm going to do is we need to do this test without any RF, and luckily this amplifier has a feature on it that allows us to do this particular test, to make these manually switch without applying RF power. And it's got a unique little socket on there, which is for keying remotely, and it's this little socket there, and all we do is we just basically stick a probe in there just to short out the inner and outer, and then these relays will manually click in. This is what's called a manual key input. So what that will do, it will negate us having to put RF in here and obviously make it key up into what would be a full-blown amplification mode. Now obviously if we've got 40-50 watts of UHF RF on here and we're trying to measure with this meter, it's going to severely damage it, disturb it. It's going to cause all sorts of problems. The cables themselves are going to act like antennas as well, so we're going to get 50 watts of UHF RF energy radiating on the bench just in front of us as well, which will cause massive interference and problems in the workshop as well as out there in the wide world, because these will act as antennas, and it'll disturb the meter and cause all sorts of problems. So and not very good for your health either, radiating 50 watts of RF just centimeters away from your body. So what we're going to do is we're going to do this test without having RF. So I'm going to I'm just thinking now, yeah, because I need this probe. Right, so I want to do a continuity test between the inner and the coax there. So I'll just go on to there, and when we put it into transmit mode, obviously when RF's coming out, and this is not going to play ball, then what's going to happen is we're going to key it up, and I knew that had happened. It starts springing off. There we are. We're going to key the transmitter mode with a manual key, and I'm going to go onto this side of this capacitor there, just on there. So basically what we're going to get is we're going to get a situation where we've got hopefully continuity through this relay. So one side of the relay, this side, controls the DC to another relay here, that one, and this side of the relay is the RF path, which goes through underside this armature and comes out the top here to this coaxial cable. So when we key the device manually and I go there, we should in theory get a 0 ohm or near 0 ohm short on this track there. So the relay should join them together. Now I can manually push the relay in myself, and obviously we can, with my manual push, we've got a continuity there, and by pushing that in, it's obviously controlling this relay as well. So the DC for this must switch the DC for that. So if I, as you can see there on the left, so that sort of proves it with a manual press, but I'm not sure how strong the magnetism is on that armature, whether it's going to pull that contact in enough, because it depends on how powerful the electromagnet is in the relay. So that's the advantage here. We're just going to now analyse that. So what I'm going to do, I'm going to introduce a short circuit, if you like, on that little key socket, that 3.5mm key socket, and then we're going to force it into TX. So like I've got a little bit here, and I think that should go up the connector and cause it to manually key. Right, so that's pushed in now, it's manually keyed, and let's see if we've got continuity, and we do. So that proves that the relay is held in. Now we shouldn't have continuity there, and we don't have that, so that means the other path coming out the relay is still isolated. However, when I unkey to simulate receive mode, the transmitter, we shall get continuity there. So that proves that the receive signal path from the antenna will get to there. Presumably it will get to there if the amplifier is not switched in, and it does, and then it would also should be able to get to there, and it does. So that proves that the relay is okay in transmit and receive mode. I was sort of hoping it would be the relay that was stuffed, or the contacts, and thus it's, you know, it would be the cause of the problem, which would be a nice easy fix. But my life's never as simple as that. So here we go. I'll key it again manually, and if I just get the damn thing to stop in, yeah, that's it. Right, and now on there, I've obviously got that short. Now if I tap the relay or do anything with it, I'm not getting any, you know, change in resistance or whatever on the meter, just at the back there. So to me that looks like it's pretty sound, is that relay. So I don't think it's down to the relay, which is a shame. So the other thing I can do is I can remove this RF capacitor here, tilt it up on one end, this end, so I can point it up so the island at the right side is facing upwards, and I can solder a coaxial cable there and the braid can solder to here, this ground plane, and the inner, the coax, can solder to the other end of the capacitor. Or I can measure its value and get another capacitor and solder that in, and then I don't risk damaging this. And then what I can do, then I can feed that coax directly off to the test set to see what the transmit power is there. So just in case there's any RF arcing going on with some solder joints underneath the board, potentially that could happen as well. Although I would have thought that we would get some definite signs, some smells, some sounds, some arcing sounds, possibly even some coronal discharge, but I can't detect any of that going off. The other thing it could be the transistor itself that's breaking down, although I doubt that. It could be that there's some dry joints, and as the current is gone up to 12 amps or thereabouts, that it's causing some heating somewhere in one of the joints. Although I would have thought the current would drop off if it was dry joints, because the resistance would be higher, and therefore the current wouldn't be able to be consumed, and the current's remaining constant. So that does seem a little bit strange. So not sure what's going on with this, but either way I can't see any automatic power control, whereas on some devices you could get a series pass transistor that controls a current to the collectors of a driver transistor. I can't see that on this device, though there could be something underneath that I can't see, where if it detects a high VSWR or it's not, something's not quite right, it'll reduce the collector voltage to this. But I can firmly see there's a connection, permanent supply going there to these, both these transistors, so it's impossible for the collector volts on the transistors to reduce by some kind of control mechanism. So it could be anything from a dry solder joint through to failing transistor maybe. It could be anything, so we're just gonna have to dig a bit deeper. Although I would have said if it was a failing transistor it wouldn't be drawing 12.5 amps. If it was a dry joint it wouldn't be drawing 12.5 amps. It might initially, until the dry joint warms up and then its resistance increases, and we get that sort of electrical arcing, arky-sparky, and then it produces a lesser voltage getting to where the collector of the transistor is, and thus, you know, that way the current would drop off, the RF power would drop with it, but the current's remaining constant, so there's something not quite right. I don't know. I might do some more tests around this area. I might test this now, the transmit input via this relay here, because when it goes into TX mode, the signal coming in here has to come out on there, and that's quite an easy test I can do now. So I can click this probe onto that resistor, and if I can get on it without it dropping off, because everything's short lead length as usual, and got to be careful as well, the device is powered up, so we don't want to cause any short circuits. And this is a real pain to get on. They've not left me much, if at all any, cable there to get on with, so what we're going to have to do, we're going to have to do it manually. So it's keyed up now, that's in manual mode. There we are. So I should get continuity between the coaxial cable input. That's where we can do it. I can go onto the coaxial cable input. This keeps dropping off. Let's just unplug this RF cable here. So what we'll do, we'll unplug this RF cable on this side. Again, I don't want to upset the CalMOS amplifier by feeding voltage up it, so we'll click onto there with this probe, and then with this one I just want to go there just to double check we've got continuity. Now in transmit mode I just want to check the relay connects the signal path to the junction of this pi attenuator, and it does. Doesn't connect it there either. That will only do it when I unkey. There we are. And then when I key, so that's receive path, that's isolating, and then the transmit path, obviously we've got continuity there, continuity there. So that, it's not as if there's some high resistance in the relay contact here, which is we're giving RF drive, and it starts to rapidly you know, drop off, and thus the power coming into the attenuators. You know, suddenly slumps. So, interesting. I think the next step is to unsolder the surface mount cap. That's just here. That little surface mount cap there. Get the RF coax on there, and let's see what happens. Rule out everything after the relay then. We should never know, there could be a fault after the relay when the RF level is there, the high RF voltages are causing an issue, or some component after it that's perhaps causing an issue. So we could look at that, rule out everything onwards in this area, and see how much power we get. It could be that we've got a cracked capacitor, that when it's warming up with RF power, the RF power is dropping away. But again, I've got this thing where I've got a constant current. You know, if I had that scenario, I'd expect IVSWR and the current to change to the transistor, but the DC conditions are not changing as far as current's concerned. So yeah, a bit of head scratcher this one, but onwards and upwards. Okay, now we've established that the relay contacts are in good working order. I thought what I'd introduce now is a new piece of test equipment, the bird through line meter and the DC power supply, because before we couldn't see the power supply on camera, so I've introduced both of these. The reason why I've introduced the bird through line meter is because it's an analog meter. It gives us more accuracy regards to any changes in the RF power more instantaneously, rather than a digital representation of it on the Rohde Schwarz. I also wanted to rule out any settling issues where sometimes radio test sets, when they're given a burst of power, can sometimes initially read a little more power than there's actually there before it settles again, and then gives us an average measurement. So I just wanted to rule out that as well. But what we can do, we can have a look at the current consumption versus power. So what I'll do, I'll introduce the RF power now to the unit to drive it, and then we'll look at the scale on the bird through line. Now we're on the 50 watt scale, and 50 watts is the second scale down from the top, which is highlighted at 50. So full scale deflection is 50 watts RF at 433 megahertz. So what we'll do, we'll just switch the RF on, and we'll get it going up to about 40-45 watts there, and then it starts to drop down to 20, about 15 watts now. So switch the RF off, put the RF back on, and then it does this every time. Switch the RF off, back on again, back up to 40 odd watts, then starts to drop off. Now I've had a look round off camera at the solder joints on the base collector and emitters of these power transistors, and as well as that the RF capacitors as well. Looked at them very carefully under a magnifying glass, and just ensure that all the solder joints are all okay, which they are. So there isn't a problem with any dry joints as far as I can see. There could be a DC bias issue set by these two potentiometers, but this problem does look more like a tuning issue to me. I've had this before on other amplifiers, and it's to do with the negative feedback arrangements on each transistor. Obviously we've got an LCR network which connects the collector to the base, and so we've initially got an RF inductor, a resistor, and then a blocking capacitor to prevent collector voltage from getting back to the base. DC wise, the DC conditions, but the RF conditions can pass back, so there's some proportion of the output power being fed back obviously to the base, and this has the effect of obviously dampening the transistor and controlling it more and settling it so that we don't get the undesirable effects that we have with amplification with severe harmonics. So it could be that if the amplifier's been mistuned, i.e. somebody's been fiddling with it before me, then it could be that all the tuning's off, and of course initially when it comes up and we've got all the reflections, the impedance mismatches and the negative feedback, then the amplifier will start to settle down, and so the settling function will then reduce the output power. Now, as I said earlier, there isn't an ALC control on this as far as I'm aware, unless it's done by the biasing. Now, I don't think there's any bias applied to these transistors in FM mode, only in SSB and AM when the switch on the front has been pressed in. But we will check that shortly anyway. But I am going to start looking around at these capacitors and tuning them to see what we can do, as well as the biasing circuit. Because I've got a funny feeling about this amplifier being messed about with by somebody else. So the only reason why I come to that conclusion is because having a look at these capacitors under the microscope, some of them have little drops of nail varnish on them, which you can't see at this level, but like this capacitor here had definitely got clean plates on it when it was in its current state of adjustment, which means that it's been moved at some point from its original position. So it's as if somebody's been messing about. So we'll just have to look into that. It may not be an electronic fault, it might be more to do with RF tuning, so that's what we'll look at next. But yeah, so the current, as we'll also see, does shoot up and then come down, or 9.7 amps, and then as the current seems to increase as the RF power comes down as well, nearly to 12 amps, 11.32 amps. So there's definitely something going on, I think, with the tuning. So we'll have a look anyway at that and see what we can do. So that's the next phase. So I'll just switch the RF power off for the moment. Now the biasing, we can have a look at that. But I just wanted to have a look at that RF power meter a little bit more closely on that. So if I introduce the RF power, and then it starts to drop. So as we can see there, we're on the 50 watt scale obviously. Power removed. So if that was an electronic fault or something more serious, a failing transistor, something like that, we wouldn't get such a quick recovery, because the temperature's increasing all the time when it's in amplification mode, and that temperature doesn't run away, exhaust itself as quickly as I'm reintroducing the power after I've switched it off. So if it was a thermal runaway issue or an issue with the power transistors failing, it wouldn't recover as quick. The amplifier would have to completely cool, and then it would then regain back to its original power, whereas in this case that's not happening. So that makes me think that there must be something more to do with the impedance tuning on the devices as opposed to a failure. So let's just come back out again. I do want to take a bias measurement on the bases of these transistors. Now obviously I'm going to have to manually key the amplifier into transmit mode by introducing on this little socket down in the bottom right there a short, which will then manually key the amplifier into transmit mode. Reason for that is because these probes are like antennas. The moment I go onto the base, or what will be certainly the base on the power transistor, there'll be many watts of RF radiating off this cable, and it would upset the meter, if not damage it, and it will give us a false reading anyway. So I don't want RF present while I'm doing this measurement, so we can have a look at that a bit closely as well. So I've got the voltmeter in the background down here, as we can see down there. Now I might be able to introduce a little bit more more light onto that for us, and that way then we can see that a little better. We've got DC volts set at the moment. All I need to do now is introduce the little shorting plug on the back of the amplifier, which is this little device here. So that's now keyed up, I think, is it? Let's have a look. Yeah, that's it. That's in the transmit mode. Now it's only drawing 335 milliamps, so that's not too bad. And then what I want to do is just, because I'm about 2 feet away from the amplifier with the camera, so I'm just trying to see if I can get onto the ground plane down there with that probe, and then go on to the base of this transistor. So get 618 millivolts roughly there. So we have got some bias in there, just under 0.7 of a volt, and 687 millivolts there. So the biasing looks correct. Now that, I don't think that matters whether it's in SSB mode or... So it looks like even in FM mode it's got biasing applied. So that's okay. That looks about right. So I don't think I need to adjust these two potentiometers down here. I think the left one is for the driver transistor, the right one's for the PA. So I'm just going to leave the biasing alone for a moment. So I think what we'll do now, we'll reintroduce the RF signal and we'll try and do some adjustments of these capacitors. We'll peak them for maximum RF power as much as we can, all of them. This capacitor, that capacitor, this one, and this one, and that one. So we've got a total of 1, 2, 3, 4, 5. Now this capacitor up here, I'm not too worried about that because that's on the pass-through for the TX path. That's nothing to do with the amplification side. That's just to tune the strip line and the pass-through of the relays when the amplifier is in the off mode and it's in pass-through mode, which we'll have a look at later. So what I'm going to do, I'm going to reintroduce the power now. We're going to watch the birdie, and we're then going to peak these coils so much as we can. Now we're using an RF trimming tool where just at the very end of this trimming tool is a little adjuster. So it's not a screwdriver, although it looks like it. It's actually a hollow plastic tube, is that, with a tiny little piece of metal at the end to adjust it. So we don't want a screwdriver because that would act as an antenna and it would be radiating RF off it. Plus with this, if this was a shaft of a screwdriver, then by touching that with his fingers we'll get an RF burn. So we'll be having, you know, close on 50 watts RF into our fingers, and then we'll be letting go pretty quick because of the immense pain we'll be in. So this is why we use RF trimming tools, special devices for adjusting the capacitors, so that we don't get 1, an RF burn, 2, it doesn't act as an antenna, and 3, it allows us to adjust it without affecting the capacitance by touching the capacitor with a probe. So they're designed for that purpose. Okay, so we'll reintroduce the TX power, and we're getting that settling again there. Look, it's starting to drop off. So I'll just tune from the large capacitor here, and I'll just see if I can get that in on camera. I might need a magnifying glass for this because, as I say, the camera and me are about 1.5 feet away from the device itself, so for me to try and see where that's going is very difficult at the best of times. This is one of the issues that we've got when we film these repair projects, is trying to see what the hell we're doing. So I'm just going to use this magnifier, and I can see that now where we are with that. So just try and get on. It's looking a bit unprofessional, but this is how it is. So we're going to peak that capacitor there. Oh, look at that. Seems to be just bringing itself up without me so much as really touching it. Now we'll go on to this capacitor there. Now again, trying to see what the hell I'm doing. Again, very difficult at times from this sort of distance. So we're getting 50 watts continuously at the moment. So I'm just trying to get on. Perhaps I should have used a shorter trimming tool. Peaking that up. Try this one now. So it's keeping a steady 50 watts. I don't know if I'm able to get any more power out of it. It's possible, of course, you know. Might want to get 60 watts, maybe more out of it, but I should have used a different trimming tool really than this damn thing, because it's almost impossible to go onto this trimmer thing. Matter of fact, let's unkey it and use a proper smaller trimming tool. Back shortly. Right, we're back. This time we've got a proper trimming tool, so we're not faffing about. Right, so we'll reintroduce the TX power, and this time, if you notice, it's not starting to drop off, is it? It's got to 50 watts straight away. So we'll go on to this again, and let's just see where we can peak that. Maximum RF, minimum current. I'm keeping my eye on the current meter at the same time. I'm currently running at 9.5 amps. Okay, so we'll now go on to this one. Peak that for maximum. This is at 433 megahertz. 9.6 amps, 50 watts roughly there. So just turn the trimmer tool around so that we've got the pointy bit, so we can adjust that for tune for maximum smoke. So that looks like as if it's doing not too bad. Let's just faff about the biasing, see what the biasing does. Anything, this potentiometer on the right side, so the biasing off there. Not really affects it much, to be honest with you. I'll just put it back to where it was, which is about there. Then the driver bias, obviously this will affect it more in SSB mode, so we'll have to do an AM SSB measurement. Drawing 9.929 amps and within 50 watts. Now if I disconnect the RF drive a second, because obviously things are getting hot. This is quite warm to the touch. I wouldn't say you could burn your hand on it, but not far off. And let's just feel the RF load. Oh, the RF load's quite warm on the bird through line, so just leave things to cool down a moment. But if we reintroduce the TX power again just for a second, just for a short duration, it's coming up to 50 watts. It's staying at 50 watts now, so that confirms it isn't an electronic fault with a component. It's somebody's been faffing about with it. It's just quite interesting. So it seemed to be mistuned for some reason. I don't know why, but it does seem a little bit strange. Does that? So it could just be that somebody's been messing with it and detuned it basically. Now I'm just going to confirm something, because the ALC, if anything, will be controlled by this potentiometer, this one here, because the directional coupler that's here goes through this potentiometer. So if I just go on to that and all I'm seeing is the LEDs on the left. If you look here, these power LEDs changing colour. So that you obviously calibrate this, but it's having no effect on the RF output power. So it's just the indication. So when it's doing 50 watts, it would read the end there, and obviously the less power it's doing, the LEDs will count down. So we can simulate that by reducing the RF gen level coming into the amplifier to reduce the, there we are, look. So that's sort of 10 watts, you get one indicator on, and then at 20 watts probably there, 2 indicators on. 30 watts you get 3 indicators on. 40 watts you'll get 4 indicators on, and then, you know, right up to 50 watts. Now, no matter what you do when you adjust the level, you can't get the red LED right at the end to illuminate. It doesn't do that because there's a red LED right at the end there. That doesn't illuminate that, so I'm not sure why. Maybe if it's doing more power output, 60 watts or something, then it will be in the red. Maybe that will be too much. So yeah, it does seem a bit strange, I must admit. So yeah, so it's maintaining its RF power, and when I switch it off and then back on again, it's keeping that RF power. So that sort of does really confirm that it was the tuning as opposed to an electronic fault. So that's something to look out for in future. So what I'll do, I'll let the amplifier cool down now, because obviously things are warmed up. I'll let it come back to room temperature. I'll put the cases back on the relays, and we'll put it back to where it was before. Then we'll do some more measurements and set up the preamp as well as the AM SSB side on the amplifier as well, with the biasing pots, and take it from there. Okay, so what I'm going to do now, I'm going to rekey the transmitter just to check that it doesn't settle again, which isn't. 50 watts, no problem, at 9.6 amps. I'm just going to introduce a bandwidth measurement now, where we're going to go up in 5 megahertz increments, and I'm just going to see whether or not so that's 435. That's again 440 roughly. Just have a look. 443. That's 443 megahertz. So we're on 433 megahertz. So that's 448 megahertz roughly, and we're doing about 30 watts. So that's 443. That's 436, 433, 428 roughly megahertz. And then we'll go down even further and see what sort of, that's 423, 418 megahertz, 413 megahertz, 408 megahertz, and then obviously it really falls off at 403. So that's 480, 408, 413, 418, 423, 428, 433. The power's still at 50 watts. 438 megahertz. It's okay, but when we hit 443, drops down to about 42 watts, and then 448 really drops off then to around about 29 watts. So good for the 430 to 440 band anyway. So that's 433 megahertz again. So that's just a quick look at the bandwidth of the amplifier, and I dare say we could tune it, you know, put it on a higher frequency and then tune these again, which might be worth doing at around about the 440 megahertz range. But we are at, obviously, if I introduce that's 443 and it's doing 40 watts, and that's now 438 megahertz and it's doing 50 watts. So I'm not going to grumble about that, to be honest with you. So I'll just do an AM measurement now and see what performance it gives at that, and look at the biasing. Okay, so we've switched this amplifier into SSB mode now, and we are going to we set up the SIGGEN already at the bottom of the Marconi to 433 megahertz on LSB lower sideband, and we've set up the Rohde Schwarz radio test set here to SSB TX test to LSB lower sideband. We've got 1K mod as well that we'll be introducing from the test set below, and I've set up the bias conditions already on the bases of these to give 0.68 of a volt, and we're just going to look to see what kind of distortion that we've got here measured there, as well as look at the mod and look at the TX power as well, just to see what that does. So I'm going to switch on the signal now, and well, it tunes in and gets best range. So it's looking good, looking good. I mean, we've just got about 30 watts there on lower sideband, and we've only got 1.6% distortion, which is pretty good. So I'll just go on to upper sideband and then change this to upper sideband as well. And still looking good, looking good. So don't see any problems there. I think everything's fine, and no need to make any further adjustments with that. We're good to go. So that's the end of the sideband adjustment. So I think we've tuned the amplifier for maximum RF power on FM. We've checked it on lower sideband and upper sideband. That's okay. We've just got now to do this low noise amplifier and something to do with this capacitor with pass-through mode. We'll have a look at that next, and we'll probably put the track gen on this and look at the performance then of the low noise amplifier for the receiver, and see what that does. Okay, so before we go on to the low noise amplifier test, I just want to make sure that we set the amplifier up so that when it's driven with 1 watts of RF power, say from a handheld device or something like that, that this potentiometer triggers the amplifier to go into amplifier mode. So we need to inject a signal into here, 1 watts RF, and set this to trigger the amplifier, so that we'll know that if a handheld with low power is connected, say 1 watt, then it will be enough to make the amplifier function. So what we're going to do is we're going to get the output of a CalMOS amplifier on the purple cable connected straight into the Rohde Schwarz test set. Now what we're going to do is we're going to introduce now a signal into the Rohde Schwarz from the amplifier, and we're going to just turn that volume down a bit, and what we're going to do is we're going to measure the RF power. Now, bearing in mind, of course, we need 1 watt, so we need to reduce the RF gen level on here to give 1 watt then out of the amplifier. and then we'll couple that into our amplifier under test. So just adjust that down to as part of 1 watt there, which that'll do it, just maybe a smidgen less, so that'll do. Right, so what we're going to do now, we're going to disconnect that signal, and then we're going to unplug this, not forgetting of course to terminate the output of the RF amplifier into the Rohde Schwarz test set internal RF load. So basically then we're not running the amplifier into an open circuit, which will not do it any good, and must always make sure we terminate that into the radio test set. So that's what we've got now, the output there, and then we need to reintroduce the input again, and we'll turn the power on as well, and that way then we can actually power it up, and we will then very carefully connect the N-type up, and now we're ready to see whether it gives it any drive, it actuates it, and we can fine adjust that as well on the potentiometer down there. So we'll reintroduce the RF power there, so it does trigger it, and it's currently giving, with 1 watt drive, 40 watts output. So just want to set this potentiometer so that it triggers it at 1 watt. So that's off, so you can see that there's power there but there's no amplification, and then that's on, and then there's a very sensitive point just there, so just adjust it. So that's just point where the Schmidt trigger triggers, and then that's on there. So I'm happy with that to be adjusted there. So obviously 1 watt RF power coming in will then mean that the amplifier will be triggered into amplification mode. Now the next thing that I want to do now is to switch the amplifier off, so there's no amplification taking place. Indeed, we'll even switch the power supply off as well. And so the 1 watt of RF power now is currently coming in this RF connector. It's passing through this relay first because it arrives here. It's going through this on this strip line, and then it's going, this strip line is being tuned by that capacitor. Then it goes through this relay and connects onto that bit there, goes across into this relay and then out to the RF socket. So we're going to have to adjust this capacitor here to tune this strip line so that we have minimal through loss. So if we just look at the Rohde Schwarz test set again, and what I'm going to do is I'm going to physically turn that capacitor while we're looking at the Rohde Schwarz test set. So just keep an eye on the RF power there. It's currently 585 milliwatt. I'm just going to adjust that, hopefully to get maximum RF power. So in other words, minimal loss. So 1.8 something 89 watts. So 1.089 watts is a maximum. So that's minimal loss now, pass-through mode between obviously the input and output. So this isn't attenuating any RF signal currently that's passing through, and it's tuned properly so that RF signal can pass through with minimal loss on transmit. So we're not going to lose any RF power going through. And obviously if I increase the RF drive as well, then naturally the output of the amplifier will increase as well. So there we've got, 4 watts of RF passing through without an issue. So that deals with that. So not only have we tuned the amplifier in the amplification mode, both on FM and sidebands SSB, but we've also adjusted the trigger to accept 1 watt RF power coming in for the amplifier to go into amplification mode. We've also dealt with a pass-through mode as well, for the transmission while the amplifier is off. Likewise the receive path coming back in this format will mean the received signal will go back this way as well, even though there's no power to the amplifier, because as we saw earlier, when the amplifier relay covers were off, the moment you introduce RF voltage by the DC, by giving it supply, this relay pulls in and connects the RF path anyway. What would be, depending on whether you've got the amplifier mode set on the front, the preamp mode, which is this button down there. So that will then divert the RF path through there. So that's what we're going to do next. We're going to divert the RF path using this relay through the low noise amplifier, and the LNA amplifier is what we're going to be adjusting next, and that hopefully should be accomplished by using the track gen on the spectrum analyzer to measure its bandwidth. Then we can adjust the gain and bandwidth of the amplifier using those capacitors, and perhaps manipulating some of these transformer windings there, these coils, so these inductors, spread them or put them close together, can have an influence on how its performance works. So that's what we'll do next. Right, we're ready to make a measurement now using the ESA series spectrum analyzer. I'm going to use this today because it's a different piece of test equipment. We're always using this one above, and this one seldom gets used, so I thought we'd have a tinker with this. Now, before we get to this stage of making any RF measurements using a spectrum analyzer, a couple of things really. One, that it's got to be on for at least an hour before you make any measurements, just so that the temperature stabilizes, the crystal oven, if it's using its own internal reference, stabilized, and that the instrument's settled. Secondly, it would be a good idea to run through all its calibration sequences and alignments, where we use the cal output on the spectrum analyzer and link it to the RF in, and also for the track gen and the RF in to be linked for the other stages of the alignments that align the track gen. And once all the alignments, auto alignments, are carried out, and you've done all those, and the spectrum analyzer has not flagged any test errors up, and that it's passed all its self-tests and its self-calibration routine, then we're at this stage where we're at now, where we're able to now just make a measurement. Now, one of the things that I'm going to show you is the reasons why we're going to do the next step to calibrate out the attenuation of the system cables that we're going to use in this measurement. So all the cables that connect to the amplifier from the spectrum analyzer and connectors all have losses, obviously, particularly at UHF frequencies. So I'm just going to demonstrate that first by using a short jumper cable, which we've got here, which we're going to connect between the track gen output and the signal input, and then we're just then going to generate a signal, a sweep across the UHF band of between 400 to 500 megahertz at 0 dBm, and we're then going to measure this, take a measurement of the level to ensure that it does meet 0 dBm, and then we're going to introduce the cables, and we'll see the differences then, and that will bring it home to you just how important this measurement is. And then once we've seen those differences and we know what the differences are with the system cables, then we need to adjust the spectrum analyzer so that it cancels that difference out. So then when we do make our measurement of the amplifier, the low noise amplifier in the RF power amp that we've got under test, then we're getting a true reading of its gain, and that's what we're going to do with this measurement. So first of all, we're just going to connect these signal connectors up here, these N-type plugs. The threads are very close on these, very tight tolerances, and sometimes they're a devil to get on because these cables that I've got are Huber Shunner cables, and they're really high spec aerospace defense grade cables, so they're not the sort of ham radio rubbish or anything like that. They're top quality cables, and the tolerances on the threading of the connectors is very fine. Okay, so we've got that cable connected now, and we now need to set the spectrum analyzer up. So we'll just take a zoom in on the screen here a little bit, see if we can get a bit closer. and maybe also get the controls in at the same time. That'd be quite nice. Okay, right, so what we're going to do now is I'm going to set up a frequency first. So the start frequency, because we're already in the frequency mode, if we weren't, you could press the frequency button. The start frequency we're going to set it to 400 megahertz, 400 megahertz, and the stop frequency we're going to set to 500 megahertz. Okay, so that's defined the bandwidth of the signal measurement we're going to take, starting at 400 and finishing at 500 megahertz. Now we're ready to set up the track gen. So we hit the source button, and then we've got the amplitude, we've got on or off, sweep mode, everything's all there, track gen offset. Now you'll notice the source amplitude is set to -10 dBm. That means when we're actually doing a signal sweep, the RF level leaving this port is -10 dBm. So every measurement we make from there on in, we'll have to incorporate that -10 dBm loss. So the signal level is -10. So for example, if we had an amplifier that had a 10 dB gain and the spectrum analyzer marker level showed that it was 0 dBm, the output of the amplifier, then we would have a 10 dB gain. So you know, you could keep that if you wanted to, but I normally work to 0 dBm level. So that means that the top line, the reference level, is set to 0 dBm. So the very top line of the graticule here is actually going to be 0 dBm as per the reference level. Now we can change the reference level if we want, but I'll leave it as it is just for the time being. So what we'll do, we'll set the amplitude to on, and as we can see there, the line's gone to the very top. Now you can do what's called a tracking peak at this stage, and then what that will do, that's particularly useful for very wide bandwidths of frequency, not so much for small bandwidths of frequency, in this case 100 megahertz, but if we were scanning from 9 kilohertz to 3 gigahertz over the entire sweep of this instrument's capability, then that tracking peak would be quite useful, because characteristics of cables, connectors and the system components all change slightly in characteristics, velocity factors of cables, etc. So the tracking peak would help minimize any discrepancies in the measurement. So we've got currently there a source amplitude of 0 dBm, sweeping a frequency of 400 to 500 megahertz. And if I now introduce the marker by pressing the marker button here, and then we can see where the marker level is, it's reading 0.47, sort of 3 to 6 dBm. So just under half a dB loss in this cable setup there. Right, now what we're going to do now, we're going to connect the cables of the system that is going to do the test. So we've verified that there isn't an issue with the calibration. We've verified that the output level as per the TrackGen output is the same more or less of what we're getting in there. There's no major discrepancies, that's what that's getting at. So now we can disconnect this test cable that we've used to make this measurement, and we can connect the system cables up that we're now going to connect to our device under test. And you'll see in a moment, because what we've done, we've joined the cables together. We have a purple cable and a black cable, which would represent the in and output of the amplifier, and we've got a joiner here which joins the two cables together. And so if we introduce these cables to the because obviously these are varying lengths, we've got the purple cables about a good metre in length, if not more, maybe 1.5 meters. The black cable just under a metre, so we've got nearly 2 meters of cable and numerous gender changer adapters as well. And so we just need to see what losses that has and then take that into consideration. Now again, a bit of a tight fit because these Huber Schunner connectors are very good quality and very precision threading. Okay, so now we've got a system reading. And if we have a look at the screen a bit closer, we can see now that we have a system loss, which is indicated in the top right hand corner just here, and the system loss is minus 1.42 something dBm. So that's telling us that the cables that we've introduced is having an effect on the RF performance, and is thus giving attenuation of 1.4 something dBm. Now we can eradicate that from our measurement by going to amplitude, and then we can go to this reference level, and that's not what we want. We want what's called reference level offset, and which is that one there, reference level offset. So we'll select that, and we can actually key in, it's averaging about 1.425, I'd say, dBm. So if we enter in the 1.425 dBs, then as we can see now, the marker offset is 0 dBm. So we've now, if you like, factored out the attenuation of the system test cables, and that means then we're not having to try and add that level to the measurement we were going to take, because if we're adding 1.42 something to whatever measurement we take, it can make things a bit more complex. And as well, that figure can change as well as we go across the frequency range that we're spanning. In this context, because we're only dealing with 100 megahertz, which isn't a great deal, the characteristics of these connectors and cables isn't going to change much at all. However, if we were going from 1 gigahertz to 3 gigahertz, for example, or 9 kilohertz to 3 gigahertz, then we would have a substantial amount of changes across the board, and we would use the normalized function of the track gen to try and eradicate a lot of that. We'd have to pay particular attention at particular frequencies as to what losses there are in the cables and connectors when we're doing our measurement. But in this context, we don't need to do that much, because if we go to marker on the spectrum analyzer, and if I can find the button again there, marker, and we move the marker whilst keeping an eye on that reference level in the top right, we can see that right down to 400 megahertz the reference level isn't changing much really. We're sort of talking tenths of dBs really, so very high spec. So it's not changing. We haven't got like waves and peaks and troughs, and it's not going up and down, is it? So that's what we're wanting to avoid. And you would get that typically on lower quality cables such as RG58 or cables that's not suited for UHF frequencies. Very lossy cables would cause all kinds of problems. So that's why you need to use really high quality coaxial cables. So now we've done that and we've factored that out, now we're ready to connect to our amplifier under test, and that's what we're going to do now. Okay, so now we're ready to make our measurement. We've connected what is the track gen output from the spectrum analyzer to the antenna socket on the amplifier. The transceiver socket would now connect to what is the signal input to the spectrum analyzer. So really it's a switch reversal to what we were doing earlier in the transmit PA measurement we were making, where we were sending a signal in on the bottom connector, it was amplified and then passed out on the top. But because we're now in the receive mode rather than transmit mode, signals which come from the antenna back into the amplifier need to be amplified by the low noise amplifier, or passed through via these relays directly, bypassing the amplifier and fed out to what is the transceiver's radio receiver, which will be connected to the bottom connector. So really we switch them the other way around, so that's worth remembering when you're doing these measurements. Okay, so obviously we're feeding a swept signal, we need to feed in a swept signal between 400 to 500 megahertz on the top connector and see what comes out on the bottom. We'll leave the preamp switched off at the moment, so it's in pass-through mode. If we take a closer look at the amplifier, we can see it's general configuration. We've got this relay, and this relay. So basically in pass-through mode, when the low noise amplifier, which is in this section here, the preamp as it's known as, isn't enabled or switched on, the RF signal basically leaves this trace at the bottom. After it comes from the antenna cable, it comes in through the relay, comes out on this track here at the bottom, into this relay, and comes out again on this track, and goes into this relay, and then comes out on the top left connector into the RF coaxial cable, which comes back down to the output, and then it goes back out to the radio transceiver we've got connected in. Now if you look very carefully on this track here going across, we have a variable trimmer RF capacitor just here, which will tune the Q of all this strip line going from left to right. So we'll need to pay particular attention to that, and I'll come to that later. Now additionally, when the amplifier is switched on, the low noise amplifier, the preamp, this relay would click the signal path from this print here to this print, which we can just see there. Now if we zoom in a bit closer, so we can see that a bit better, perhaps we can get the camera to play. What we've got two Schottky diodes which are clamping the input to prevent any over voltage. Really that's useful particularly when the amplifier is used with an external antenna that's in close proximity to other antennas, which can then couple high level RF back into the amplifier and thus cause the saturation of the amplifier or overdrive it. Static electric, all kinds of issues that can come into the amplifier and cause issues can be suppressed all in these back-to-back Schottky diodes, but basically therefore clipping, compressing the RF coming in so it doesn't go above a particular level. Then we've got what appears to be an RF transformer. So we've got this piece of wire here which is bent in a position where it's straight and then solders down to the RF ground, which is the signal ground, the ground plane, which is this bonded track here which goes up to this area and connects to the screening cam as well, which divides the amplifier. We've then got a secondary winding here which is basically another inductor that runs parallel with it, again suspended at the same height, which solders to this island, which connects to the low noise amplifier device, which is either a mimic, a monolithic microwave integrated circuit, or a bipolar transistors with BFR90, BFR91. I don't know if it's a BFR bipolar or a mimic at this stage because I can't see any biasing arrangements until I really look at it under a magnifying glass, but that device amplifies the signal basically. So on the opposite side of the device as well, we've also got another inductor here which then goes to this island, and then we've got what appears a radio frequency choke, and this looks like a 5-volt voltage regulator. So the 5-volt voltage regulator would supply 5 volts through the radio frequency choke, allowing DC to pass through but choke off any return RF from coming back. It would then enter this wire, the DC supply voltage, and connect to what is the collector of the RF transistor. So any amplification that takes place will be passed on to this inductor, and we'll be tuning the Q of this inductor with this fixed capacitor just here. So this looks like it's been tuned at manufacture, so they move this capacitor up and down this wire to tune for maximum RF output at the required bandwidth. So this isn't an RF transformer as such, it's just an LC circuit decoupling DC block to allow the RF to pass through onto this tracker on the top and then out through this relay. Now, interestingly enough, on the input as well as the output, we have tuning capacitors which we can tune using the trimmer. So we can obviously tune this up. Now we can manipulate this RF transformer to some degree by either pinching the primary and secondary together, or separating them even more, or manipulating the gaps, because it's an air gap, it's RF transform across from the primary to the secondary winding. We're not really going to play about with this so much by moving this capacitor up and down, because I say it's been tuned at manufacture. Notice on the output there appears to be some kind of pi attenuator with a look of it, so maybe to suppress any harmonics or to reduce the gain of the amplifier. They've chosen to use what looks to be a pi attenuator there. And on the output, 2 more Schottky diodes to clamp the output to prevent any high level spurious emissions to leave the amplifier, or to clamp anything that might be on that rail that's above 0.7 volts. So it's quite a basic amplifier, not too complicated, but obviously we now just need to set this measurement up on the spectrum analyzer. So in pass-through mode, what we're going to do is we are going to set up our track gen now. So we'll go to source on the thing. We'll switch the amplitude on. We are using 0 dBm, which may drive this low noise amplifier into compression. So that's something we're going to have to consider when we're doing harmonic measurements shortly. So we'll switch the spectrum analyzer's track gen on. Now, as we can see, it's quite lossy. If I put the marker on, that's incredibly lossy, is that. Minus 14 dBs in pass-through mode. So we'll go, the only thing that could be wrong here is either we've got an open circuit RF path, i.e. one of the relays has got dodgy contacts on it, for example, or it could be this capacitor here, because I think that somebody's been tuning this and faffing about with it before it came to us. So this capacitor tunes a queue of the transmission line that comes basically from the input to the output on the amplifier. And if I can get this damn trimming tool to go on the end of that capacitor, and if we watch the performance, so we need to get that to minimal loss really. So looks like it's coming up. Need it to be as flat as possible and minimal loss. So I think the most we can get there is just 2. We need it as low as we can, 2.89, 2.9. It's round about there. Can't get any better. We've got a little bit of a trough just there. It's not too much to worry about. Minus 2.9 dBs of loss. So in pass-through mode, that's as much as we're going to get out of it, and obviously that's the internal losses of the amplifier. If you remember earlier, we've already introduced a 1.43, I think it was, dB correction factor for the RF cables that come in and out of the spectrum analyzer and connect to the amplifier. Now we need to also introduce another correction factor into there, which is this loss here. So this is the system loss of the amplifier. So basically all the plugs and connectors, the relays, the 3 relays, all the print track, this coaxial cable, all adds up to an internal system loss of just under 3 dBs. So we now need to add that to the 1.46, I think it is, what we'd already added. So let's say 2.92. It's hovering around about 2.92 dBm. So that will be about 3. Let's have a look. 2.92 to 1.48. So when we add that all up, that will be around about, if we say that's 3 dBs, 4.4 dBs of loss. So if we go to what is amplitude and add, I think it was reference level offset, it's already at 1.43. So say if we add, make it 4.43 dBs, 4.43 dBs. So that now will correct our level. As we can see now, we've factored out because we've returned back to almost 0 dBm, if we go back to the marker, what we've done there, we've factored out, taken care of all the losses now in the system. So we've taken care of all the cable and connector losses going to the spectrum analyzer. We've included the internal losses within the amplifier as well. So when we make a measurement of a low noise amplifier, we're actually looking at the gain of the low noise amplifier. We're looking at the actual gain of a low noise amplifier, not the actual gain plus all the losses, which will then tell us lies. So we've obviously got to know what this amplifier is actually doing to its absolute limits. So that's why we have to factor all these things out. First of all, we're factoring the cable losses out, and secondly, we are removing the internal losses of the RF amplifier from the measurement. Right, so here we go. So now I'm going to introduce the amplifier output. Notice we're 20 dBs down because it's 10 dBs per graticule. If you'd set the spectrum analyzer up so that on the reference level, so this line was on the top line here, obviously when we introduce the amplifier, then it will disappear off the top because the gain of the amplifier exceeds the level at the top of the graticule. If a graticule at the top is set to 0 dBm, for example, and the amplifier is 10 dBs gain, then it will be 10 dBs higher than the top line, so it will vanish off the screen. So that's just worth remembering. So attenuate the amplifier output basically by going to amplitude, and then as we can see there, we've got a reference level of 20 dBs, which puts it 2 graticules down. If that was 0 dBs, it'd be at the top, obviously. And then when we put the amplifier on, we wouldn't see it, and we do want to see it, so obviously, you know, that's worth knowing. So if we go back to marker again, right, so we're at 0 dBs. Now we're going to switch on the amplifier, and as we can see there, there isn't that much gain there, if at all any. So now we can faff about with the tuning of the input output capacitors. So basically these relays are switched now, so the RF path is going via the amplifier. So if we go on to what is the first capacitor, which is on the base or the input to the low noise amplifier, which is just below, because there's a screening can obviously in between, and then we need to introduce this from, well, adjust it for maximum gain. So that's what we're doing now. So, oh, it's a bit tricky, this capacitor. Got a fair bit of noise. Some capacitors have 2 peaks. So we'll just turn it full circle again and see what this is. Oh, that's quite, this is a better part of a capacitor there. So I really want the marker not to be at 450 megahertz. I want it to be at 433. So we'll adjust the marker down to 433 megahertz. And if we can get the frequency spot on, because it is a bit tricky. Right, now then, I'll adjust that capacitor to peak it at 433 megahertz. So here we go, let's just get on the damn thing again. Very carefully adjust it, it's very sensitive. Let's just see if we can get the other peak. There we are. Oh, look at that. There we are. Well, I never. Right. Okay, so right, so that's still with the amplifier on. We've got a nice peak there, much as we're going to get. We're not going to get any better than that. So now we're going to the output capacitor, the output of the amplifier, low noise amplifier, and we'll just adjust this now for peak. So I think 7.349 or something, around about there. 7.7 something or other, about there. That's maximum I'm going to get it. Now we could go back to what is the input again, just to see whether we can get any better than that. I don't think so. I think that's about it. Now we could manipulate that RF transformer, these RF transformer here, to see whether we can increase or decrease the gain. So if I try and pinch that transformer together there, so we can, it's just altering its frequency, starting to, as you can see there, increase the frequency rather than decrease it. So we'll come back out again. We're not really increasing its performance, are we? If we come way out, it's really bad, the gap, as we can see there. We can fit a trimming tool in between. It's not really improving it, so we're not getting any more gain, basically. That's what I'm trying to say. So I'll move it back to its original position, which is there. So we're not going to get any better. That's the peak of what we can get. Had we had got the amplitude to have increased, say, at a lower frequency or higher frequency by manipulating that RF transformer, then I could have just adjusted the capacitors to then move the frequency peak back to 433 megahertz. But because we couldn't establish any higher peak than we've currently got elsewhere when we're manipulating that RF transformer, there was no point in trying to go any further, because we're not going to get any more out of it. So the total gain that we're getting at the moment at that frequency is 7.39 dBs of gain. Okay, so now what we can do, because we've done all the RF measurements on the amplifier we can do, what we need to do now is to have a look at maybe the harmonics now of what it's performing. So without the amplifier switched in, obviously we're getting a nice flat response across the frequency band. With the amplifier switched in, we're getting 7 point something dBs of gain. Now we can go to delta. We can set up the delta marker, and we can now calculate the 3 dB points for the bandwidth. Now there may also be a mode on the spectrum analyzer that allows us to do that as well. I'm not sure if it's a band pair, but we can have a look. So delta, so with the peak is 433 megahertz at 7 point something dBs. We just need to lower the frequency now of the marker, so we get the 3 dB point, which is roughly about there, I would say 3.1, give or take a bit, 2.9 something. It's hard to get it exact, but with a little bit of patience you can do it. It's just a lot of faffing about, roughly about there then. So we'll say 19.8 megahertz below, okay, which is 413 megahertz, okay. So if we go back to 433 megahertz there roughly, which was the peak, then increase the frequency then to get 3 dBs again. So the 3 dB point is there, give or take. So that's 21.5 megahertz, which is 454. So it's quite a wide bandwidth, that very wide bandwidth, more than covers the 77's ham radio band and beyond, so for its amplification. So that's its bandwidth. Now if we look at the harmonics, bearing in mind of course this amplifier doesn't have a filter on the RF input or output, which professional amplifiers would have, so it'd be interesting to see what the harmonics are like. So if we go to measure, I think it is, it'd be interesting to do the occupied bandwidth. Oh, here we are, look, that's it. Occupied bandwidth 2.968 megahertz. Start frequency 448, stop frequency 451. Occupied bandwidth power 99%. No peak found, it said, so I'm not sure. Adjacent channel power measure off. Just interesting to faff about, see what we can actually get. Harmonic distortion, there we are, look. So now we can look at the harmonics this low noise amplifier produces. So interestingly, it's chosen a frequency of 450 megahertz instead of 433, which is just there. In which case, at that frequency, at 450 megahertz, it only achieves a gain of 5.2 dBs. However, the second, third, fourth, fifth, and sixth harmonics then are at these levels here, which is minus 24, which isn't bad really, and all the rest of these figures are quite good, considering we're actually saturating the amplifier with 0 dBm, or equivalent to 1 milliwatts of RF power. So that's actually quite a high level of signal. So that's the harmonic content of the received low noise amplifier. Now what we can do now is we can progress to do the same measurement, but this time using the transmitter side of things. So we'll need to attenuate 50 watts of RF power down. So what we can do is we can measure the TXPA side of things for the harmonic measurement, because we haven't done that. It'd be interesting to see what the harmonic content's like coming out of the amplifier in transmit mode as well. But at least that gives you a breakdown at the moment of doing that measurement, where we've had to take into consideration there the system losses of the cables, the amplifier. Then we've while the amplifier is not enabled, the low noise amplifier in the preamp, we've then adjusted the internal tuning of a device in pass-through mode for optimum flatness across its frequency bandwidth and minimal loss, where we ended up with just 2.9 something dBs of loss internally within the amplifier. Circuitry, relays, the print, the coaxial cable connectors. We'd also factored out the cables as well that connect to the amplifier, and we essentially took those two correction factors and added them into the spectrum analyzer to correct for that, and then we enabled the preamp, and then we tuned the preamp then for maximum gain across the widest frequency range we could achieve. And then ultimately we finished off there with the harmonic measurement as well. So again, the harmonic measurement is important, but again the specification for what the harmonic should be for this particular amplifier will probably be in the service manual or the instruction manual, but they're not at danger levels, because if they were, they'd be highlighted as red levels, so the harmonic content will be way too high, and potentially then we'll be driving the amplifier into compression. So we may have to choose a lower level of signal coming out the track gen, so we're not driving the preamp into compression and thus causing it undesirable effects. So that's something else to consider as well when you're doing measurements on low noise amplifiers using a track gen. Right, so onwards and upwards, we'll move on to the next stage now, transmit harmonic analysis. Okay, just to discuss this circuit diagram, essentially the low noise amplifier. I've had a look under the microscope of the low noise amplifier device, and it is actually a bipolar small signal RF transistor. It isn't a mimic because it's got some biasing to it. So basically coming in, as we saw earlier, we had the relays, the RF relay, and that basically made connection there. We had the bypass bit, and coming in from the RF relay we had the Schottky diodes, which were back to back, and we can draw those in this formation. And they both went to RF ground on one side and the signal on the incoming, and then from there they went straight into a transformer, which will draw like that, and then going down again to signal ground. Now then, on the output of this transformer, because that's the primary, this is the lower wire there, and the upper wires are secondary. Because it's an air-gapped transformer, we don't need at these frequencies to have any cores, iron core, ferrite core, anything like that in there. It's just an air gap, and the RF will transform across. And then if you remember rightly, we had a variable trimmer capacitor, an adjustable radio frequency trimmer capacitor, which one side went to chassis ground, and we had its variable adjustment, which we adjusted with a trimming tool. That went in then straight into what is the base of this, what looks to be an MPN sort of BFR 91 RF small signal transistor. This looks as if it's got a biasing arrangement on it as well. So we had a resistor connecting from the collector and the base down to a signal ground 0 volt basically, and then coming along the top here we had a supply on there, which we'll derive later on, and we had basically another inductor here. And if you remember, we had the capacitor, which could effectively slide up and down the secondary, if you like, or this inductor here on the output of the amplifier. So that would be the collector, that would be the base, and that would be the emitter of this small signal transistor. So we had a tap off this inductor to a capacitor, which then led off as our signal output. And after this piece of wire, which goes along here, we had another radio frequency choke, which is this red coloured winding here, which has actually got a ferrite core in it. So we'll draw that in this fashion, and then inside it has a ferrite core, and then that went to a voltage regulator, which no doubt will have plus 13 volts on the input. That obviously go to ground, and this will be 5 volts output, and that was as a 7805 series voltage regulator. Now the output of that voltage regulator as well had a second tap off it just before the radio frequency choke, which then supplies the base or the biasing. Now, following on from the signal output, it then went into what was a pi attenuator, and so we'll draw that in that formation, which were those chip resistors we highlighted, which were only very small. And then that went into what was Schottky diodes, again very similar to the input, back to back, orientated in this fashion, where we basically have them clamping this RF line for obviously any if the amplitude on the output is beyond a certain level, it will clamp it, prevent any wild swings in voltages, etc., potentially coming off this. Should that occur, or it be driven into saturation, it wouldn't be able to develop a voltage in excess of 0.7 volts. These are fast frequency switching diodes, because potentially this transistor can actually be an RF power transistor, maybe hundreds of milliwatts, maybe 500, 600 milliwatts output, possibly even a watt, if driven with too much RF power. And so that could actually cause damage to a receiver. So we need to clamp both the incoming and the outgoing signal so that it can't go above a certain level. Because these transistors are used in all kinds of different applications, not just small signal amplifiers. Depends what they are. Likewise, the clamping on the input there is quite important, because if you've got a situation where you've got an antenna on a, say, a radio tower or radio mast in close proximity with another antenna which is used for transmitting a high level of RF signal from, if the two antennas are quite close together, then coupling can take effect between one antenna and the other, particularly in situations where you've got mast with multiple antennas and you're transmitting at high levels off the others, and that RF can couple to the antenna that's connected in here, and then we can get undesirable amounts of RF coming in at different frequencies into this transistor, and it can obviously then upset the whole circuitry, and you don't get much separation between UHF at one frequency and UHF at other frequencies, or VHF or even HF. So you need to have that ability to clamp an incoming signal which is potentially very, very high level, which could potentially either damage the transistor or alternatively saturate it, drive it into compression and cause all kinds of undesirable effects. So that's why they use these clamping diodes as well. And on the output of the devices, which I've negated to add here, directly across the collector to what is the RF ground, was another variable capacitor which would tune the output. So that's where that was, and that was again the second variable capacitor that we tuned. And this obviously went off then to what would be the relay contact then for the output. Now, insofar as the bypass was concerned, we had obviously all these relay contacts and things, and effectively we had a strip line going via what would be several switches, and again, just to draw this effectively with the configuration that it was in, again we had another 3 relays in total, and then we had a tuning capacitor, again variable tuning capacitor across to chassis ground, and these effectively went to the input and the what would be the output RF connectors. And so essentially that capacitor which was here, this capacitor there, tuned this effective line, this transmission line, through all those different relays. So that's basically a little rundown of what it is that we were looking at just 2 minutes ago. It's worth noting as well, when we discussed this area in particular of the device, where we've got this long piece of wire, if you remember, when we look just here, we've got this long piece of wire just here. In RF terms, this is actually an inductor. And then what we're doing then is we're taking a tap off it, in essence, and that then will be our RF output. This side will go to plus volts, which will be in our case 5 volts DC, and this side would obviously go to the collector of the transistor, and that would obviously go to ground on that side. So effectively we're swinging on the collector, we're swinging the RF voltage via this inductor. So when we look at it, it's just a piece of solid wire, but in RF terms it's an inductor. It's a coil. It's just like this radio frequency choke is here with the red wire. So obviously at 450 megahertz or thereabouts, then that is, you know, a big piece of wire, a big piece of inductance. So naturally the capacitor would tune the Q of this inductor by moving the tap on the capacitor, on the inductor rather, up and down its length. We can then impedance match and also produce the maximum level of RF coming out that the transistor can amplify. You'd think if we moved it more towards the collector, we'll get maximum RF, where in actual fact, depending on the impedance that we're driving and the Q of the circuit, would probably make that not happen if we got too close to the collector. Likewise, if we move a capacitor too close to the supply line coming in, which is more to the other side of the long piece of wire, because obviously you just got a piece of wire, that's all, and a capacitor, which is our big square thing, and we can just move this up and down, you know, this wire in effect. But basically it's a big inductor, is this piece of wire. It doesn't look it when you look at it with your eyes, it's just a piece of wire, but at UHF frequencies that is an inductor. So, you know, naturally you're moving it up and down to get the best performance out of it and to tune it, its Q. So that's a little rundown of that. It's just how you look at it sometimes. You think, well, how can that work? It's just like having two pieces of wire, one running parallel with the other, both bonded to ground or signal ground on one side, and one connecting, obviously giving an RF out, and one with an RF input coming in. In essence, RF coming this way onto the inductor on this side of this air gap transforming effect, works its way onto the other side, and then obviously we're getting a signal coming out, and we can manipulate that and move it. But in actual fact, that physical construction is actually this, insofar as the circuit theory is concerned. But to people who are not very familiar with RF, that just looks like a dead short and a piece of wire, and how the hell can that transform RF across it? But you've got to remember, at UHF frequencies, even short lengths of solid wire of particular gauges can be massive inductors. So at UHF, and particularly at UHF frequencies and above. So, you know, that's where it gets quite interesting, and sort of the black magic side of RF. Okay, when we're measuring RF power directly from the output of the amplifier, and we need to feed it into the spectrum analyzer, obviously the spectrum analyzer has a rated input power handling capacity, which must be taken into consideration. And if we look at our spectrum analyzer, we can see that it's got a warning telling us that it can take a maximum of plus 30 dBm, which is equivalent to 1 watt RF power. So we must attenuate the output power 50 watts down to below 1 watt in order for the spectrum analyzer to read the RF level correctly. Now, it's very important that we don't exceed 1 watt, or we don't come anywhere near 1 watt, and I'm not happy about using any spectrum analyzer near its rated maximum power. So we need really to be no more than, say, 100 milliwatts in my mind coming into that spectrum analyzer to prevent any damage. Now, yes, the spectrum analyzer is rated at 1 watt, but we're not going to use it at that because that would be a silly thing to do. So what we need to do is we need to introduce attenuators, and there's a couple of ways we can measure harmonic output on the amplifier. If we have a directional coupler, for example, which is the safest method of measuring RF signals at high power, indirectly, because we've got a transmission line going across the bottom, and then we've got a coupler which is a close proximity sniffer to the main transmission line, which has got an output connector here, and this is I think it's 20 dBs below the carrier power. So in other words, you know, we can couple minus 20 dBs coupling. So that can instantly give us the capability to connect the spectrum analyzer to this port, and then obviously transmit power in from the left side, so it couples most onto the port that way, so it's reading forward power, not reflect, and then dump this side into a load. And then what we're doing then is we can calculate the minus 20 dB attenuation on the spectrum analyzer like we did earlier, and factor that minus 20 dB out in the offset level parameter, so we can actually read RF power at full level from the amplifier on the spectrum analyzer, because we're asking the spectrum analyzer to take into account that level of attenuation, and thus it will compensate for that. Even though we've only got, say, 100 milliwatts leaving there, the spectrum analyzer is able, because we know what the loss is in this coupler, to make up for that difference and thus measure the fundamental power coming in on the left here from the transmitter. That's the safest way of measuring high powered RF, because the isolation is so high between the fundamental RF coming in versus the coupled sniffed RF, that it's not a direct measurement, it's an indirect measurement of the fundamental RF, the incident RF as it's known as. So the limitations of this obviously is when we're doing harmonic measurements is how good a performance this is across those harmonic frequencies. So if this is only engineered to work between 400 to 500 megahertz, it's no good then at measuring harmonics that are higher than that, because its performance can't measure at those frequencies. So if you've got a harmonic at 2 gigahertz, for example, the coupler may not work at those frequencies. So you need to know what the coupler's performance is. If a coupler can work from 400 megahertz to 3 gigahertz, then, you know, Bob's your uncle. You can use that and it will measure the signals across all the harmonic ranges up to 3 gigahertz, and that may suffice in your measurement. So that's where things get a little bit complicated, is that it might be minus 20 dB at one particular frequency band, but then at other frequencies higher or lower, for example, then it won't be minus 20, it'll be a different value, and thus it'll make your readings all out. So you need to know about what the spec is of these, but they are the safest way to measure high powered RF without having to attenuate it and then introduce that to the spectrum analyzer. The other way of measuring is by direct measurement, which is by employing high powered RF attenuators. These are Bird RF power attenuators. This can take 100 watts continuous power. So naturally, if we were to choose an attenuator that could only attenuate 50 watts of RF power, that would be a very silly thing to do to use it in this particular context, because the RF amplifier is 50 watts. This would burn out, or it will be near its maximum. It would overheat and it would then change its characteristics as it gets hotter. So therefore it'd be a silly thing to run something to its maximum. So I tend to use attenuators where they are effectively able to attenuate a signal well within its capabilities. So 50 watts in this case is half the rated power of this RF attenuator, so it's not going to get too hot, it's not going to burn out, and it's not going to change its characteristics, because obviously it's running at its maximum all the time. It's only running at 50% of its total tolerance. Now you can get attenuators in different levels of attenuation, but what I like to do to keep things nice, rather than have one attenuator that's capable of attenuating 50 watts down to say a couple of hundred milliwatts for the use on the spectrum analyzer, what I like to do is, instead of this having to do all the hard work all on its own, and obviously to attenuate that kind of RF all the way down in one go will get this quite hot. So this is a 3 dB attenuator, and for every 3 dBs we half the transmitter power. So if we start off with 50 watts coming in on one side, we'll have 25 coming out on the other at 3 dBs. So then we can reduce the power obviously below 50 watts and then feed it into another attenuator if we wish, and this particular attenuator has a maximum input power of 50 watts. So by coupling in 25 watts, again half the rated power of the attenuator, it's not going to get too hot, it's going to last for long measurement times, and then the output of this, the being a 30 dB attenuator, means then the output level is well below the level needed for the spectrum analyzer's maximum threshold. So by using 2 attenuators, then naturally we can reduce that level down. The other thing about it as well is, God forbid you should connect the attenuators the wrong way around, for example, because that is possible. Some pi attenuators, or in this case these attenuators, are not bidirectional, so they have an input side and an output side. It could potentially mean that if you were to connect them the wrong way around, if you're using one on its own rather than 2, then you could potentially damage the attenuator, and also there's a potential, depending on the attenuation chosen, where the output level would be excessive for the spectrum analyzer, and it would damage the spectrum analyzer. And it's a bit like, you know, metalwork and woodwork. If you you know, measure twice, cut once. You know, if you cut it wrong, you've had it. You know, if you cut too much off a piece of wood, you can't put it back on, you know. So you puff the spectrum analyzer and that'll be it, bang, and that's a lot of money down the drain. So rather than make that mistake, and obviously in case there's any undesirable things, such as we've say testing an amplifier that can do 150 watts but we're only testing it to 50 watts, you need headroom, so that if for any eventuality that you weren't able to plan for the RF power suddenly peaking at 200 watts due to a signal generator measurement being too high, or you press the wrong button on the test instrument and it overdriven the amplifier and then it produced momentarily 200 watts of power, by using one attenuator you risk obviously having the output power of the attenuator being in excess of what the spectrum analyzer can cope with. So I tend to go with a safety margin where we employ 2 attenuators for that reason. So if, for example, we're sweeping the RF amplifier, it does 50 watts at one frequency and 150 watts at another frequency, because of some unexpected thing that we've not taken into consideration, drive levels, voltages, mistakes in measurement, things like that can happen quite easily. You can blow up your test instruments. So by using 2 RF attenuators means that with half the power to start with, we then more than halved it again by increasing the level of attenuation. So therefore we've got a major advantage there with headroom. This amplifier can produce as much RF as it wants within reason, and because we're using effectively 33 dBs of attenuation between the two, means that effectively this would vaporize before the output level of this attenuator was exceeded the rated input to the spectrum analyzer, and thus it would not blow the spectrum analyzer up. So that's why you've always got to be very careful when you choose attenuators. Remember, for every 3 dBs we introduce, we half the output power of the transmitter power amplifier. So 6 dBs, again we have it again, another 6 dB, making it 9. You know, we have it again 3 times, we'll halve it if we have 9 dBs of attenuation. So we'll halve it 3 times. So the more attenuation we have, the better. And always work within those very fine tolerances in the spectrum analyzer. I have a rule where I don't put more than 50% of the rated input power of an instrument in its socket, input socket, because it's, you know, we need that headroom. We've got to have that headroom. If a measurement goes wrong and something happens where the output power goes through the roof suddenly, then you've got to make sure that that level does not exceed the input level to the instrument that you're using to measure that RF signal. So what we need to do now is we need to connect these together along with the associated RF cable. We need to sweep them on the spectrum analyzer to confirm the attenuation. So we've got the orientation correct. As you notice, this is marked input and output, but on some of them they're not marked. So you know, if you get them wrong way around, you might not get the right level of attenuation. It might be less, so therefore you'll cause damage. So we need to sweep them first to make sure that they have got 33 dBs of attenuation. There isn't a problem with our connections. We need to attenuate, take into consideration the attenuation of the cables, and then we need to write that figure down on a piece of paper so we don't forget. And then that is effectively what the correction factories will enter into the spectrum analyzer later on to get the absolute accurate power measurement. As I say, for every 3 dBs you attenuate a signal, you half the power. So with all the errors that there might be 0.5% here or there between the 2 attenuators, whatever the attenuation is on this cable, it can make quite a difference to your measurements. That's why you've got to measure the all system components together first, so you know what the losses are, and then you make an absolute accurate measurement. Otherwise, 0.5%, half a dB here, 1/4 of a dB there, soon adds up when using multiple components like this, and thus the measurement can be incorrect. So that's where we're going to go next. Okay, Okay, so we're ready to make a measurement now using RF attenuators on what will be the output of the device under test, which is the RF amplifier. And obviously we need to know what kind of attenuators and level of attenuation we need in order to use a spectrum analyzer as an accurate RF power meter, which will give us a direct power reading in watts of the RF power coming from the device under test, and also will allow us to make harmonic measurements as well at other frequencies, so we can analyse how clean the RF power amplifier operates. In this case I've chosen here two attenuators, both made by Bird, and both have a break frequency of 6 GHz, so it's more than capable of dealing with our 400 to 500 MHz frequency range. Now, because the way that we deal with RF power, and particularly attenuators, the hotter they get, the more inaccurate they become. So it's really, really important when we're making measurements that we keep the temperature as low as possible on the attenuators. So the idea of this experiment is to sweep the attenuators and all the associated test cables we're going to be using with this measurement, so we can calculate exactly what the total system losses are of all the system components, the attenuators, the cables, the connectors, any RF adapters, plugs, you name it. We need to know what that loss is, because for every 3 dBs we attenuate a signal with half its power. So if we get 0.8 of a dB loss, or half a dB loss here or there, that can make a big difference to our measurement, because you don't need much attenuation for it to make a marked difference in the output performance of the device under test in our measurement. So we need to make sure before we measure the transmit power amplifier, we sweep with all the components that we're going to use in the test to get a figure. And as we can see here, we're sweeping a frequency of 400 to 500 MHz at 0 dBm, which is leaving this port here and then going through the attenuators and coming into the signal input port, and we're getting a figure of minus 33, call it 0.8 dBm or dBs, 33.8. So I've written that down on a piece of paper, so I won't forget that for later on, because we're going to enter that into the spectrum analyzer as the reference level offset like we did earlier, as a system loss of this particular components. Now also you'll notice that the way that we've got the RF attenuators orientated in this measurement is quite important, because these pi attenuators that are high powered are not bidirectional. Some are, some aren't. I've got some here that are made by different companies that I'll no doubt show my channel some other time that are bidirectional. If you turn them one way around, the say 9 dBs of attenuation at a particular power level, and then if you turn them the other way around, then they'll give you a different level of attenuation at a different power level. Other RF attenuators, like this one for example, they are not bidirectional. They have a designated input and output connection, and also you must orientate them the correct way around when we're making measurements, both with the spectrum analyzer and the device under test, because obviously we need the signal that's leaving the spectrum analyzer on the sweep gen to come into the input of what would be the connection to the transmitter, and the signal output from the end of the attenuator chain to go into the spectrum analyzer. If we had them the other way around, we will get different readings, and ultimately when we come to then connect up to our device under test, we could cause damage to the attenuators, and that's what we want to avoid, because these are very expensive. So this Bird through line meter here, Bird RF attenuator rather, is rated at 100 watts input power. So obviously if we're dealing with 50 watts, then it means this attenuator is not going to get very hot, which means its characteristics are going to remain more or less stable. And likewise the output power of this attenuator, then if we've got attenuating by 3 dB, which this is, will mean it's 25 watts. And the next attenuator in line is a 25 watt input. Now this particular attenuator is rated at 50 watts, so again we've got a 50% headroom yet again, so this will be kept nice and cool as well. and this gives 30 dBs of attenuation. So what comes out of here is attenuated by 30 dBs again. So the total system attenuation between the two attenuators is 33 dBs, but the 0.8 dB, as we're getting in the measurement here, the minus 33.8, is down to the system losses of the cables, connectors, plugs, and that. So it's very important that that 0.8 of a dB is equated in our measurement, is added in, so that we're calculating that as part of our measurement. So the spectrum analyzer gives a perfectly accurate reading then of the device under test. Now, the other thing that we've always got to be careful of when we choose attenuators is we need that headroom, which, as I've said earlier, is in this case chosen to be 50%. The reason for that is because we don't want, for example, an error in our measurement where we're testing a power amplifier and, say for example, at one frequency it does 50 watts and at another frequency it does 120 watts. And we also don't want a situation where if there's an error in our power supply, where at one voltage it's doing 50 watts and at another voltage it's doing 70-80 watts. And thus we want a sufficient level of attenuation to allow that headroom and power rating so that we don't exceed the attenuator's capability and thus burn them out because they're quite expensive. And secondly, we want to ensure that the input power to the spectrum analyzer signal input is at least 50% below the rated maximum. So with this part being rated at 1 watts power between 9 kilohertz to 3 gigahertz, we don't want to exceed 500 milliwatts coming in, and I would never advise anyone to exceed half a rated input power of the spectrum analyzer's input attenuator because it can cause damage, particularly on long measurements. Sometimes when you read the manuals on these spectrum analyzers, they'll give momentary power readings. So for a momentary period of time, like a power burst, say for a radar transmitter or a digital transmitter, where we're dealing with sort of QAM or a pulse modulated signal, then the power rating can be quite high, whereas on a CW carrier wave reading, then the power will be quite low. So we don't want to test providence by putting too much power into the signal input on the spectrum analyzer. And I always work with attenuators and the spectrum analyzer with a 50% margin of headroom there, so that should the measurement go wrong or something we mess up, that it doesn't then blow the spectrum analyzer. And I also work to a very large attenuation as well. Now, as I said, for every 3 dBs we have in the power, so if we're starting with 50 watts coming in here, if we have it by using a 3 dBs, it becomes 25. If we then put in another 3 dBs, it would obviously become 12.5 watts. So that's 6 dBs of attenuation in total to get 12.5 watts out. If we then put 9 dBs of attenuation, we get 6.25 watts. And if we put 12 dBs of attenuation, we'll get 3.125 watts. And then obviously, if we go another 3 dBs above that, so we'll get to 120 milliwatts, 0.12 watts. So obviously, in a situation where we're dealing with 50 watts RF power, if we wish to get 120 milliwatts to enter this spectrum analyzer, we would need 15 dBs of attenuation. And once we've used the 15 dBs of attenuation, then we would essentially have enough headroom to make our measurement, and we would only need 15 dBs instead of 33 dBs. But it doesn't matter how much attenuation you use, even if it's excessive. It just means that the dynamic range of the spectrum analyzer would mean that you would have a lesser signal entering the spectrum analyzer with a high level of attenuation versus a smaller level of attenuation. And it's really preferences, individual preferences, but I always like to work with a large attenuation for that reason, so we've got that headroom, and should something go wrong, then we're not going to exceed obviously the rated input of the spectrum analyzer. And it all depends as well what components you've got. Some people don't have a 15 dB attenuator. I mean, I've got loads of different attenuators here, but that's 6 dBs or whatever, but it's not 15. And I do might have a 15 dB attenuator somewhere, but it's not rated at 50 watts. It might be rated at 10. So it all comes down to many factors, really: the frequency, the power, the level of attenuation that you need in, and you can add attenuators up. And the most important factor is, when you're making these measurements, is because there are slight errors and percentage tolerances between them, that you need to add that into the measurement, which is why we do this test first. But also we need to keep the attenuators cool. There's no use running attenuators where you can't put your hand on them because they're so hot, you know, you can fry an egg. Because all that means is the attenuation that they had when they were cool has now changed because the components have heated up. So we don't want that either. We want to make sure the measurement's stable. So keep things cool, even if it means putting fans on things to keep the temperatures correct. And I'll run them to such a degree where we use high power attenuators with medium or low power signals, so that the temperatures remain stable and the measurement thus remains stable. So, right, what we're going to do now, based on the fact that we know the RF power, we've decided to choose 33 dBs of attenuation. We've got the reading of 33.8. I'm going to enter that into the spectrum analyzer next on our measurement, so that when we do our next stage in the test, the spectrum analyzer can take account of the total system attenuation. So we don't actually do that in the spectrum analyzer track gen mode. So we can preset the instrument now, and the next stage of the video we'll move on to setting up the spectrum analyzer on the spot frequency we're going to use on the device under test, and then we're going to enter the reference level offset of minus 33.8 dBs, so it takes into account the total system loss, and thus we can make our RF power measurement. So that's the next stage of the video. Okay, we've connected the power amplifier now to the second attenuator, or the first attenuator in this case, and the second attenuator is connected to the signal input of the spectrum analyzer. We've preset the instrument, so it's not going to take into account of any previous changes in measurements. Okay, so we'll set up the frequency first to our test frequency of 433 megahertz. We'll set the span to 1 megahertz. We will then go to the amplitude, and we'll set maximum amplitude, because obviously the signal, I think it's about 55 dBm there, 55 dBs of attenuation. So when we're putting the power in them, you know, we can see it'll not be off the top of a scale. And then we need to go to under amplitude again, reference level offset. This is where we need to enter that 33.8 dBs of attenuation. That's the figure we measured earlier, if you remember, of the total system loss of the attenuators and cables. Then we need to go to the y-axis units and change that to watts. Okay, and now we're ready to make a measurement. So what we'll do, before we switch the amplifier on, we'll just look at the drive power going to the amplifier first, and we will then put the marker on, and we're reading 3.9 watts there, which is what my Calmus drive amplifier provides. Obviously, if we were driving the amplifier harder at 5 watts or 10 watts, which is what it's rated to, then we will get, you know, well beyond 50 watts output from the device. But I think with about 4 watts drive, as we were looking at earlier, just around about 40 watts, something like that. You get 50 watts out of it if you drive it harder, but obviously you get more harmonics as well potentially coming out. So we've got 3.7 watts drive. Okay, so now I'm going to switch the amplifier on, and then we can measure the total carrier power there. So the amplifier is on now, and reading 39.8 watts roughly. So I can go to span and do a 0 span, and then that will then now tell us what the actual top of that peak is, which is 43 watts. If I just go to view display there, full screen, I can zoom in on the screen for you now, so you might be able to see with a bit more detail. But as you can probably see there, we're getting, as we can see there, 43 watts. So that's how much output power the spectrum analyzer is currently doing. 43, well, reading 42.78 watts, something like that, just under 43 watts at 0 span. Obviously, if a span was set wider, say to 1 megahertz, then the RF power would read less, because we're not actually on the top of that peak really. We can move a mark ever slightly, but because of the units are measured set at 401 points, it'll either go over one way or the other, and it won't be bang on the peak as such. If you got it down to something like 50 kilohertz or somewhere about that, the sweep would obviously slow down. But really, for measuring accurate measurements, it's 0 span. And then obviously span, if I can do it. Have I messed it up already? Span is 0 hertz, and now that will give us the absolute power measurement on that frequency, which is reading 50 watts. 49.7, 50 watts. There you are, look. So we're actually getting a bit more power now, because I think we just varied the frequency ever so slightly onto that peak. It's probably to do with a number of points as well. It's reading 401 points per second. So, you know, obviously its accuracy varies slightly, but 49 to 51 watts there, as we can see in that top right hand corner. Okay then, so let's have a look at the harmonic analysis next. Okay, so now we're ready to look at the harmonic analysis. So just with the drive power alone, preset the instrument, which gets us back to this screen. We'll do amplitude change now, just so that we can see these signals. Obviously, if I switch the drive source off, they disappear, so we know they're valid signals that are not internally generated. Then what we need to do now is we need to set the frequency up, where we set the start frequency to 400 megahertz and the stop frequency to 3 gigahertz, which is the extremes of the instrument, the upper frequency limit. Okay, so what we can do now, there's two measurements, two ways we can make the measurement. We can either do it manually by this mode, or alternatively we can go into the menu and select the harmonic analysis there as well. So first of all, we'll look at the manual way, and we'll just introduce some more attenuation, so that when we switch the amplifier on, obviously we can see that there's a harmonic coming in. So if I go to for example under display full screen, we can see, if I just increase that a little bit, we can see that we've got the fundamental, which is at the far left, and then we've obviously got a harmonic. Now if I get the marker a second, and then we just move a marker, I can see the marker. There we are, look, marker 1. So marker 1's frequency, if I can just get it to go to the top of that peak. Well, we can do peak find, peak search. That's obviously at 433 megahertz. Next peak. Peak search. Marker. Thought it might want to go on to the next peak. So the next peak is there. That's 875 megahertz. So basically it's double the frequency. So the next harmonic from the fundamental is 800 and something megahertz. That frequency is not entirely correct, spot on, but it's in that frequency range, give or take, because obviously we've got a massive span on at the moment. As we decrease the span, the frequency accuracy improves. So what we need to do now, obviously, if I were to reduce the drive level from the amplifier that's driving this power amplifier, that harmonic will reduce, obviously because of the fact that we're giving this amplifier sort of a saturated drive. But at least we're aware of that harmonic. Now, currently under amplitude, we don't. If I make the spectrum analyzer more sensitive, we are picking up another harmonic here. Obviously, the fundamentals reach the top line. If we were to introduce any less attenuation, then it would overdrive a mixer in the spectrum analyzer. We wouldn't get an accurate result then, obviously, the harmonic content. So we'll keep the fundamental just at the top line, and then we'll select the marker, and then we'll move the marker then to that point there, and that is roughly, I just see it hovering above the that's 1.3 gigahertz. So again, the next multiple of frequency up again from what was the very first harmonic. So now that we know that, and we know what harmonics are present, we haven't got other things there. Now we can make a full measurement at full power. So this time we're going to introduce a larger amplitude of around about 55 dBs, because obviously we're now going to increase the output power from 3-4 watts drive to 50 watts. So we'll do that now. We'll switch the amplifier on, and then as we can see there, we've got a fair bit of signal there. Actually, let's just have a look. And I haven't really got much there. We've got some. Let's have a look. Display, full screen. So at this level, we've currently got, because now we're reading the level that's coming in here as opposed to converting it to watts. If I adjust the marker now, I don't know why it keeps going back to not a full screen. Right, okay then, so that, if I can just get that to the top, that's minus 37 dBm power, and that's minus 39 dBm at that frequency at 1 point something gigahertz. And then this next harmonic here, 1.733 gigahertz, minus 42 dBm, and then the very last harmonic there, we can measure 2.168 gigahertz roughly, and again the level on that is minus 45ish to minus 46 dBs. So that's pretty good. You know, we can see that the harmonics are not incredibly high, they're not in comparison to power, they're not very high in amplitude, and there's obviously a specification for that as part of the product design, and as well as that, the regulatory body limits the amount of harmonic output that a device can provide depending on its power level. Now, there are different ways of measuring harmonics in relationship to the carrier. We can measure the amplitude in relation to the noise, and also many specifications are quoted how many dBs down from the peak of the carrier to the harmonic is actually present. So sometimes they'll measure the difference between the peak of the fundamental and the first, second, third, fourth harmonics, or alternatively they'll measure the harmonic in amplitude between the noise floor and the peak of the harmonic. So that's different ways of doing it depending on the specification and tests that need to be undertaken. So we'll look at the auto harmonic analysis now, and see what we can get the instrument to provide us with data on that. Okay, so we preset the instrument again, which I've just done there. That gets us back to this screen. We'll then go to frequency 433 megahertz, which is our test frequency. We'll then go to the span, which will be 1 megahertz. Okay, so we've got that. We'll introduce some attenuation to get that signal below the top line, and we've obviously got the capability as well if we want to look at the marker level and do a peak search, so it absolutely gets it at 12.02 dBm, which is just the level coming in there from the power attenuators. Then what we need to do then, if we go back to amplitude, or is it measure? I think it was measure. Harmonic distortion. Now we can do the auto measurement of the harmonic distortion. So now it'll calculate that for us. So it'll give us a fundamental frequency. If I go back to the display and select full screen, so there we have the fundamental frequency, which is 433 megahertz, and then the subsequent harmonics at 866 megahertz, 1.3 gigahertz, 1.7 something gigahertz, 2.166, 2.590 I think it is, if my eyes don't deceive me, and 3.031 gigahertz. So basically the very first harmonic right the way through to the very last harmonic, we're looking at minus 49.3 dBcs, right the way down to minus 76.17. So the total harmonic distortion in this case is 0.48%, which is pretty good. I'm quite happy with that. It just shows that it is actually quite clean and is working within specification. So that gives a little rundown of that. Well, after all said and done, I think we've reached the end of the video now. I don't think there's much else we can do to this amplifier. Obviously we had to reverse engineer it to some extent, because obviously we didn't have a circuit diagram for it. There was no manual, no technical information, so we had to sort of work out how it worked and go through all that analysis, which we did initially as part of the start of the video. We weren't sure whether it was a component failure. In this case it wasn't. It was just the fact that it was detuned off the frequency it should have been. I think the person who had this amplifier prior perhaps tried adjusting it perhaps to another frequency out of band for what it was designed for. There's certainly been some evidence there that some of these trimmer capacitors have been adjusted out their limits. Then we analysed the measurement further in setting up the transmit power correctly with the drive and establishing a full output power and aligning all the potentiometers and capacitors appropriately to achieve that. Then we moved on to the low noise amplifier section for the receiver improved sensitivity. Obviously this amplifier has that facility. Not all power amplifiers have that. And we obviously analysed that circuitry and did the alignment as well. And obviously the spectrum analyzer in this case, we used it in many different ways, not only for measuring the transmit power, which we did finally in the end, using series of attenuators which we introduced, and looked at the measurement dynamics around cable losses and attenuator losses, and being able to factor in the internal losses as well within the amplifier in some sections of the video, where we went into detail about finding out what the internal losses were as well as the cables under test, and then factoring that measurement in with the spectrum analyzer and offsetting that and calculating that as well, which we needed to establish. We looked at the harmonic measurement of both the transmit side as well as the low noise amplifier side, and the alignments for the sweep generator. So we swept the amplifier with a frequency, a test frequency for the low noise amplifier, and adjusted its bandwidth and its gain, and measured that in dBs, yet again having factored out all the system losses and other attenuations that take part in this measurement. So again, that was quite a fruitful thing to show. And then finally we've ended up doing a transmit harmonic analysis as well on the power amplifier, using again the method of calculating system losses of attenuators and cables and taking that into account on the spectrum analyzer, and then changing the spectrum analyzer in effect to an RF power meter, where we're then converting the units of measure from dBm into watts, and using the external attenuation factored in with the measurement, being able to read direct RF power from the RF amplifier without damaging the input to the spectrum analyzer. And obviously I went into great detail in this video about how to set up the spectrum analyzer. In this particular case, the ESA series of spectrum analyzer is more or less the same to set up as the older versions of spectrum analyzer that came before it. I said it's just a little bit more detailed when you're setting up the amplitude units for the wattage in comparison to the older spectrum analyzers. But when you're jumping from one piece of equipment to another, it's actually quite a challenge really to get your head around some of the different menus, settings and things like that. But it's certainly been quite a good video from my perspective, because I've been able to show you how to make the accurate measurements with taking into account system losses, but also how to set up a different spectrum analyzer this time. And some may not be familiar with making those kind of measurements on the ESA series of spectrum analyzers. And also having gone into making accurate measurements for harmonics and looking at where that should be in relation to amplitude against the fundamental, gives you an indication of what to look for when you're looking at harmonic content, and potential there for self-oscillation and for problems to occur in amplifiers where they can run away with themselves. And we discussed earlier in the video about the moderating the flatness of the gain and stability by using negative feedback circuits. We also did SSB testing on the amplifier as well as FM measurements, and we looked at that. And so after all said and done, I think we've just about come to the end. And thank you very much for watching. If you like the video, please hit the subscribe button. It really helps the channel grow. And if you'd like to put any comments in on the video, by all means please do so, and we'll see you in the next one. So thanks again. Bye for now.